In this video, we're going to do an integration marathon. We're going to solve about 120 integrals. And so the way this is set up is that I've gathered about 120 integrals. The types of integrals that they are completely random. It's a mixture of all different types of integrals. So definite, indefinite, and then the kinds of functions that are involved. It's completely random and all different types. The technique that you need to use to solve each integral could be any one of the techniques that we've learned, but you're not going to know what technique to use. We're just going to be presented with the integral as is, and then just you have to decide for yourself how to solve it. Okay, the level of difficulty is random. It's the 120 integrals it's a mixture of easy all the way to very hard. And we're going to, again, all of these integrals are just thrown into a hat and picked out of a hat. So we're not going to start with the easy integrals and then work our way up to the harder ones. It's going to be completely random. We could get the hardest integral in the whole bunch first, potentially. We don't know. Okay, now, obviously, you're welcome to watch this video or follow along with the video working the problems yourself without having any kind of background preparation for this. You can do that, and you'll get plenty of really good integration practice doing it that way. However, my suggestion would be, if you really want to master solving integrals, I would suggest going through all of the videos in the playlist involving integration. Watch the videos where we talk about the concepts, where we go through the textbook, then watch the corresponding example problem videos and work those examples yourself. So those examples are specific to each topic, like for example, specific to each technique of integration. So we've got the integration by parts section with the integration by parts example problems, the substitution method section with the corresponding example problems, the trig substitutions, the trigonometric integrals, etc. So I would suggest watching the lecture videos on those sections, then working the example problems, and then once you've done that, come to this video, to where coming into this, you have some background on the techniques. You're familiar with all the techniques, right? There's even the video a few videos ago where we talk about the strategy for integration, how to approach if you're just given an integral and you don't know, there's no context as far as how you're supposed to solve it. How do you approach solving it, right? So watch that video before you come here, and then go through this marathon. Now, I know this is an extremely long video, and it's because integration takes a lot of practice. But if you do your preparation before this video, if you go through all those sections, do the example problems yourself, and then you come here and you have a kind of a foundation for this video, and then you go with that foundation, you go through this entire marathon and work these problems, I guarantee you will come out of this as an expert in solving integrals. Okay, so let's get started. Looking at the integrand here, we've got a power, so t to the first, times what the textbook calls a transcendental function. So this is like a trig function or an exponential or a logarithm. So we've got a power, just like t to the whatever power, or a polynomial multiplying a cosine, an exponential, or a logarithm. Those types of integrals usually work with integration by parts. Okay, but I'm just curious if we, when I see this cosine squared, let's go take a look at the trig identities. Okay, so we have cosine squared is equal to 1/2 1 plus cosine 2 theta. This might be useful because in terms of integration, cosine 2 theta is easier to work with. So let's just go ahead and make this substitution that cosine squared theta is 1/2 times 1 plus cosine 2 theta. So we've got okay, and so we can bring out, let's come over here, bring out the 1/2. And we've got okay, now let's continue to simplify. And so it looks like we're going to have to use integration by parts anyway. But so, okay, let's separate this into two separate integrals. It looks like we've got a simpler. So we can, this is easy. We can solve this. And then okay, so we've with this substitution, we've in essence broken this down into, this is a simpler integral. And why is it simpler? Because cosine of 2t is easier to work with in terms of integration. So let's go ahead and do integration by parts. We're just going to ignore the 1/2. So let's do integration by parts here. Okay, so both t and cosine of 2t are easy to differentiate and integrate. So if we had to choose, let's go ahead and differentiate t, since it'll eliminate the t. So we'll say u is equal to t, and db is equal to cosine of 2t dt. So du is equal to dt, and then v is equal to, it would be 1/2 sine of 2t, right? So all right, u times v and then with the way we do integration by parts with a definite integral, we evaluate this from at the limits, and then minus v du. So bring out the 1/2. Okay, the integral of sine 2t is minus 1/2 cosine 2t. So let's make this positive 1/4. And then okay. So sine of 2 pi is 0, and sine of 0 is 0, so this is 0. Okay, now here we've got 1/4. Cosine of 2 pi is 1. Cosine of 0 is 1, so this is 0. So this is 0. Okay, so this entire integral is just equal to this. So this, we've got 1/2, and then the integral of t is 1/2 t squared, so 1/4, and then t squared from 0 to pi. So 1/4 pi squared minus 0, so pi squared over 4. Okay, so when I see like a sine x and a cosine x, I think, you know, the derivative of sine x is cosine x, the derivative of cosine x is minus sine x, so I think u substitution. However, that's not going to work here because we don't have like sine x dx or cosine x dx. Okay, so now what I see, this denominator, this sum of two terms in the denominator of a fraction, and you know, you can always think about multiplying by the one in the form of the conjugate over the conjugate of the denominator. And yeah, in fact, let's go ahead and do that. And the reason why I'm feeling confident about this is because there's two reasons. Multiplying 1 plus cosine x by its conjugate is going to greatly simplify the denominator, and it's easier to, when it comes to, you want simpler denominators so you can separate, that makes it easier to separate out the fraction into separate sums of separate fractions. But then also, yeah, we might have some complexities in the fact that we'll get some, like a cosine squared x, but then also we're gonna go from, like, I know I'm going from cosine x to cosine squared x, and cosine squared x is easier to work with. It's more complex, but as far as with trig identities, no, it's not. So we get, this is going to be 1 minus sine squared of x, which we know is going to be cosine squared of x. Okay, now the numerator is going to be, okay, so 1 minus cosine x plus sine of x, so plus sine x minus cosine x, and then minus sine x cosine x, and then 1 minus cosine squared x. So we've got 1 plus sine x minus cosine x minus sine x cosine x. Okay, and so we can separate this. This is complicated, right? But the big idea is we've got a simplified denominator, and with this we can separate this up into separate fractions, even though this is more complicated, but we can separate it up into separate integrals. So we've got our integral is equal to 1 over sine squared x dx plus sine x minus okay, and so we've got 1 over sine squared x is cosecant squared x. This is going to be cosecant x. This we can, let's just leave this as it is, because it looks like we can make a u substitution there. Right, these are all just trigonometric integrals. And then here, cosine x over sine x is cotangent x. Okay, so let's go to our table of basic integrals and see, so we can get cosecant x, the integral of cosecant x and cotangent x. And I think we should also have cosecant, the integral of cosecant squared x. Okay, so we've got, yeah, we do have cosecant squared. And we've got cosecant and cotangent. Okay, cosecant squared is minus cotangent. So, okay, now what about cosecant? Cosecant is natural log of the absolute value of cosecant minus cotangent. Okay, and then cotangent, natural log of the absolute value of sine of x, and we'll have it'll be minus though, because of this minus. Minus natural log of the absolute value of sine of x. Okay, and then all right, so what is okay, if we say that u is equal to sine of x, then du is cosine x dx. And we can do it this time because we have cosine x dx. So we have 1 over u squared du. This is equal to what? Minus 1 over u, which is minus 1 over sine of x, which is minus cosecant x. So this is going to be here, it's going to be plus cosecant x. Okay, plus c. And there you go. Okay, so one of the methods we use when we're presented with a random integral is you can identify what category it falls into, and this is obviously a trigonometric integral. Okay, and so the combinations that we studied in the trigonometric integral section was combinations of sines and cosines, tangents and secants, and cosecants and cotangents. But it's not like if you get a trigonometric integral that it's a different mixture that that you can't do anything with it, because you can apply trig identities, and if you have a tangent, you can turn that into a sine over a cosine, right? If you have a 1 over a sine, you can turn that into a cosecant. So with the trig identities and the way the basic trig functions are related, you can morph the trigonometric integral, the integrand, into all kind of different forms until you get a form that you can solve. And in fact, that's the general strategy. So we have a combination of tangents and secants here, but if we don't have the right power that we need to solve this with the cookbook method, then we just apply trig identities and the definitions of the trig functions to rearrange it into different forms until we can solve it. All right, so when it comes to combinations of tangents and secants, we're looking for an odd power on the tangent or an even power on the secant. And so we've got both. And so, when I see secant squared theta, d theta, I think that we can say that u is equal to tangent theta. And why is this? This is because du is equal to secant squared theta d theta. And even if you had a trigonometric integral where maybe the secant or the tangent was in the denominator, right? Because what we learned in this trigonometric integral section, there was these specific cases of you're neatly multiplying these two specific types of trig functions. But the idea is the principles that we learned, you can extend those to any integrand that contains trig functions, and no matter how they're combined together. That's the idea. You could always apply trig identities and the trig definitions and rearrange it. For example, you could have all kind of things going on. The tangent could be anywhere, but if you have a secant squared theta d theta, then you can think about, okay, well, I can substitute u is equal to tangent theta. Okay. All right, but just continuing here, we've got, okay, so when theta is equal to 0, u is equal to 0, tangent of 0 is equal to 0. When theta is equal to pi over 4, we've got tangent u is equal to 1. Okay, then we've got u cubed du. Okay, so this is 1/4, and then u to the 4th evaluated from 0 to 1. 1/4 times 1 minus 0, 1/4. Okay, so here, the first thing I see is x squared plus or minus a squared, like x squared minus 1 squared. And so anytime you see a squared plus or minus x squared, or x squared plus or minus a squared, you think potential trig substitution. In particular, in the fact that we see a square root that we have x squared minus 1 squared contained under a square root, that's really what trig substitutions can be really useful for, because they eliminate the square root. But trig substitutions can be used in any situation. It doesn't have to have the square root. Just anytime you see x squared plus or minus a squared plus or minus x squared. Okay. Also with the square root, I think about potentially rationalizing this, meaning we say that u is equal to the square root of x squared minus 1 and turn this into a rational function. But to me, that would be, if we're going to go that far, then we might as well just do the trig substitution. Okay. But however, a trig substitution is something we'd like to avoid if we can, because it's kind of difficult. It's not that big of it's not difficult. It just takes time compared to like a u substitution. So, you know, well, we can't, there's not going to be a u substitution we can do here because, oh, well, maybe, because, okay, if we said that u is equal to, I'm just curious about this, because if we said u is, no, that's not going to work. I was thinking that if we said u is equal to the square root of x squared minus 1, right, then du is, and you get, right, you get this 1/2 times 1 over the square root of x, 1 over the square root of x squared minus 1, which is in here, right? But then we're also going to have times 2x. I mean, let's just see. I'm curious about this. So this is, and then dx. So this is, okay, so we have, okay, let me make sure I've got this straight here. So du is equal to x times right? Okay. So, and the big idea is this is here, right? So we've got, and so, okay, what that means is that du over x is equal to that. Du over x is equal to that. So you've got 1 over x cubed times du over x. So 1 over x to the 4th du. Okay, now what is this x to the 4th though is the issue. So we see that x squared minus 1 is equal to u squared. So x squared is equal to u squared plus 1. So squaring both sides, x to the 4th is equal to u to the 4th plus 2u squared plus 1. And so, yeah, okay, that's how you rationalize it then. So it didn't work out as cleanly as I thought. Okay, I thought that might work out a lot. I thought we might do a u substitution and actually be able to quickly get the integral, but that's one way to solve it, right? Because now we could solve this as a rational expression integral. But let's just go ahead and go back to the, let's just do a trig substitution. That should be easier. All right, so we've got x squared minus 1 squared. Here are the trig substitution options. We've got this option. We've got x squared minus 1 squared, so we want to make the substitution that x is equal to secant theta. So x is equal to secant theta. Therefore, dx is equal to secant theta tangent theta d theta. Okay, and so x squared, square root of x squared minus 1 is secant squared theta minus 1, the square root of secant squared theta minus 1, which is tangent squared theta. Which is tangent theta. We don't need to put the absolute value because of the domain is restricted, right? We talked about all this in the trig substitution videos. Okay, so we've got x cubed secant cubed theta times tangent theta, and then we've got secant theta tangent theta d theta. We're left with 1 over secant squared theta, which is cosine squared theta. Okay, how do we solve the integral of cosine squared theta? We use the half angle identity. Cosine squared theta is 1/2 times 1 plus cosine 2 theta. Okay, so we've got theta over 2 plus the integral of cosine 2 theta is 1/2 sine 2 theta. And there we go. So we've got plus c. All right, now we need to get back to the x variable. So, okay, x is equal to secant theta, so x over 1 is equal to secant theta. Secant is 1 over cosine. Cosine is adjacent over hypotenuse, so x over 1 is hypotenuse over adjacent. So, okay, this side we have 1 squared plus the unknown side squared is equal to x squared. So this is going to be the square root of x squared minus 1. Okay, now okay, 1/2 theta. Sine 2 theta we know is 2 sine theta cosine theta. So this is okay. All right, so what is sine theta? Opposite over hypotenuse. Okay, what is cosine theta? Adjacent over hypotenuse. And then theta is, right, solve for theta here. So we've got and that is the integral. And that is a little easier than it would have been to do the partial fraction decomposition. Okay, so here I see a square root with a fraction with some expression of x under it. And, okay, if we substitute like u is equal to e to the x minus 1 but there's no e to the x dx out here. And so my first instinct is let's go ahead and substitute u is equal to this entire square root with the x expression to see if we can turn this into a rational function. So we're going to say that u is equal to okay, and a lot of times when we're doing this, we would square both sides to clean this up. However, let's go ahead and just take the derivative as it is, because we're going to get right. So if we multiply both sides by 2, we've got 2 du is equal to the integrand, right? So making the substitution, you've got 1 over u and then times d. Well, no. It's even simpler than that. Just 2 du. That's it. Wow, that's pretty cool. This is just 2u plus c. What is u? That's it. And so that's so simple. We probably could have figured this out just by looking at it. Yeah. So, right, I mean, look, okay, what's the derivative of the 2 times the square root of e to the x minus 1? Well, 1 over 2 square root of e to the x minus 1 times 2 eliminates the 2. And so you're left with just 1 over the square root of e to the x minus 1. Then plus c. So, yeah, we probably could have just figured that out if we'd have carefully looked at it. But, yeah, there you go. Okay, so, I see a x squared plus a squared, especially particularly under a square root, so I think trig substitution. But maybe we can do a u substitution, but that looks like it's not going to work so well because of the, if you say u is equal to x squared plus 1, then we have x squared dx, not x dx. So let's go ahead and do a trig substitution. So we've got x squared plus a squared. That's this form here. We want to say that x is equal to, so a is 1, x is equal to tangent theta. Therefore, dx is equal to secant squared theta d theta. Okay, so if we make the substitution here, we get tangent squared theta plus 1 is equal to secant squared theta. We don't need to put the absolute value because of the domain restriction. And so we've got, and then x squared is tangent squared theta, and then dx is secant squared theta, d theta. Okay, so we've got tangent squared theta, secant theta. And so this is a trig integral, and we've got tangents and secants. And when we've got tangents and secants, we're looking for the power on the tangent to be odd or the power on the secant to be even. And that is not the case here. So what do? Well, we just apply trig identities or definitions of trig functions to just rearrange it to see if we can get a form that we can work with. So we could even turn this into sine squared theta over cosine squared theta, and this to 1 over cosine theta, and then see if that comes out to be something with combination of sines and cosines that we can work with. But what I want to do is let's go ahead and tangent squared theta is secant squared theta minus 1. Let's do that. Okay, so we've got so secant cubed theta can we work with this secant cubed theta? Yes, we can. The textbook actually, there's an example in the textbook where they solve this. Okay, so we've got secant theta is natural log of the absolute value of secant theta plus tangent theta. Okay, and now for secant cubed, we could go ahead and do this with integration by parts, but they solve it in the textbook, so I'm going to treat that like that's part of our table. Okay, so any integral that we when simplifying that we come across that's either given here or it worked as an example problem in the textbook, I'm just going to go ahead and reference it. So we see here the secant integral of secant cubed of x is, so let me copy this. All right, so 1/2 secant theta tangent theta plus 1/2 natural log okay, and then okay. So now we need to substitute back to get x. Okay, tangent theta is x divided by 1. Tangent is opposite over adjacent. So hypotenuse squared is equal to the square root of x squared plus 1 squared. Okay, so tangent theta is equal to x. We already have that here. Secant theta is, so secant is 1 over cosine. Cosine is adjacent over hypotenuse. So hypotenuse over adjacent. And that's it. We just have secant and tangent. And then we don't even have a theta. We don't have theta either. So we just have secants and tangents. So, okay. All right, let me put tangent theta is equal to x. So 1/2 secant theta tangent theta plus 1/2. So we'll put x plus okay. Well, this is, yeah, these two are going to combine, right? 1/2 minus 1 is minus 1/2. So and there you go. That is the integral. Okay, here, to me, I just think integration by parts. I mean, okay, we don't see a u substitution. That would be easy. I think integration by parts because these two are both easy to differentiate and integrate. So let's say that u is equal to e to the x and dv is equal to cosine x dx. So du is equal to e to the x dx, and v is equal to sine of x. Okay, so u times v minus the integral of v du. Okay, and so we didn't simplify it anymore. Now we have e to the x sine of x, but this is going to be one of those where we want to do integration by parts again, and we're going to get the original integral back, and then we'll end up solving it by combining the original integral with the old integral. So, all right, if we do integration by parts on this, u is equal to e to the x, du is equal to e to the x dx, dv sine x dx, v is minus cosine x. So u times v minus the integral of v du. So bring out the minus. Okay, and so what we have is if we distribute the minus sign, we're going to get plus e to the x cosine x, and then minus right? And now we can solve it because we can add this integral to both sides. And we get 2 and we can take out an e to the x and now divide both sides by 2, and we've solved for the integral. Right? Because this is the integral we're trying to solve. Plus c. Okay, so we can't make a u substitution. Like we can't say u is equal to 1 plus e to the x because we don't have a e to the x dx outside of that. And so I'm thinking about the idea of whenever we rationalize a fraction, we don't have a fraction here. However, the whole idea with rationalizing is you end up with these like polynomial terms, and polynomial terms would be easier to work with. So let's just see what happens. For when we're rationalizing a fraction, we substitute, say u is equal to the entire integral. Or the entire radical with the x expression under it. So what if we said this? Okay. Now, what we want to do is, before we were just taking the derivative straight from here, but let's not do that because we don't have like a 1 over square root of 1 plus e to the x. So let's say that u squared is equal to 1 plus e to the x, and then if we take this derivative with respect to x, we get 2u du dx is equal to e to the x. Okay, so 2u du is equal to e to the x dx. So dx is equal to 2u over e to the x du. Okay, but we see that e to the x is equal to u squared minus 1. Therefore, dx is equal to right? So what do we have? We have u times and then dx so we've got, we could bring out the 2, we've got u squared. There we go. So we've got a rational expression. And we can solve any, we can take the integral of any rational expression. Okay, how do we integrate a rational expression? Rational function. First step, check to see is the order of the denominator, or the order of the numerator, is the order of the numerator less than the order of the denominator? No, it's not. They're equal here. So we start by doing polynomial long division. U squared divided by u squared is 1. So multiply 1 times the divisor. So left with 1, remainder of 1. So u squared over u squared minus 1 is equal to 1 plus, okay, so we've got and so this is equal to okay. So now let's perform partial fraction decomposition on this 1 over u squared minus 1. The order of the numerator is less than the denominator, the order of the denominator. So we want to factor the denominator. Okay, now let's write the form of the decomposition. Okay. Clear the fractions. So if u is equal to 1, then 2b is equal to 1. b is equal to 1/2. If u is equal to minus 1, then minus 2a is equal to 1. A is equal to minus 1/2. So we've got minus 1, and then, so we can separate this into, we'll do, take out the 1/2. Okay, so we've got 2u plus natural log of the absolute value of u minus 1 minus natural log of the absolute value of u plus 1. This is 2u plus natural log of the absolute value of u minus 1 over u plus 1. But u is equal to the square root of 1 plus e to the x. So we've got so 1 plus e to the x minus 1 is just e to the x. And then 1 plus e to the x plus 1 is e to the x plus 2. So plus c. There we go. And wait, hold on. I'm sorry. This is square root of 1 plus e to the x, not e to the x, plus 2 that's the integral. Okay, wait, I'm confusing myself here. So the 2 times the square root of 1 plus e to the x, and then square root of 1 plus e to the x minus 1. The 1's don't go away. And then square root of 1 plus e to the x plus 1, not plus 2. Plus c. Okay, here I see this square root, and then inside the square root is a quadratic, right? So a quadratic being an ax squared plus bx plus c. And so with any quadratic, we can write that in a form of x squared plus or minus a squared. And with that kind of form, we can do a trig substitution. And trig substitutions are particularly useful with square roots, with that a squared or x squared plus or minus a squared under a square root, because it eliminates the square root. So let's do that. Okay, so we want to complete the square on this. Okay, so we've got minus x squared minus 2x plus 3. Let's take out a minus x squared plus 2x minus 3. Okay, so x plus a squared is x squared plus 2ax plus a squared. Here 2a is equal to 2, so a is equal to 1. So we've got x squared plus 2x, and we want to add 1 minus 3 minus 1. So we haven't changed the equation, right? So we've got the x squared plus 2x plus 1 is x plus 1 squared, and then minus 3 minus 1 is minus 4. So let's see, x squared plus 2x plus 1 minus 4 is x squared plus 2x minus 3. That's right. Okay, but now let's put the minus sign, let's distribute the minus sign, and we get 4 minus x plus 1 squared. Okay, so there we go. That we have this 2 squared minus x plus 1 squared. Now, this isn't quite the form that we need to make the trig substitution, but all we need to do is now say that u is equal to x plus 1, and therefore this is, we have 4 minus u squared. And so with that, 4 minus the variable squared, that's this form here, right? 2 squared minus the variable squared. So we want to make the substitution that the variable is equal to 2 sine theta. So we want to say that u is equal to 2 sine theta. But u is equal to x plus 1. Therefore, the trig substitution we're going to make is x is equal to 2 sine theta minus 1. So that's the trig substitution we need to make. X is equal to 2 sine theta minus 1. Okay, therefore dx is equal to 2 cosine theta d theta. So 3 minus 2x minus x squared is equal to, the square root of that is equal to 3 minus, so we've got 4 sine theta and then plus 2, and then minus x squared is going to be 4 sine squared theta minus 2 sine theta minus 2 sine theta minus 4 sine theta and then plus 1. Okay, so we can, let's distribute this. So we have a negative here. A positive here, and then a negative at the end. Okay, so we've got, let's see, minus 4 sine theta plus 4 sine theta goes away. 3 plus 2 is 5, minus 1 is 4. So 4 minus 4 sine squared theta. So factor out the 4, 1 minus sine squared theta. 1 minus sine squared theta is cosine squared theta. And so 2 cosine theta. And we don't need to put the absolute value because of the domain restriction, right? Because of the domain restriction here, that's why we don't have to put the, we talked about all this in the trig substitution section. Okay, so we've got making the substitution, we've got 2 cosine theta, and then dx is 2 cosine theta d theta. 4 cosine squared theta d theta. There we go. So how do we solve this? We use the half angle identity. 1 cosine squared theta is 1/2 plus, or 1/2 times 1 plus cosine 2 theta. So let's take out the 1/2. Okay, so we've got 2 so 2 theta plus, okay, the integral of cosine 2 theta is 1/2 sine 2 theta. And so we divide the 2, and so we're just left with sine 2 theta. Okay, but sine 2 theta is 2 sine theta cosine theta. And there we go. So okay, so now we need to get this in terms of x. So, okay, we've got 2 sine theta is equal to x plus 1. So sine theta is equal to x plus 1 divided by 2. All right, sine is opposite over hypotenuse, so opposite over hypotenuse. Okay, so if this is z, then z squared plus x plus 1 squared is equal to 4. So z squared is equal to 4 minus, and then x squared plus 2x plus 1. 4 minus x squared minus 2x minus 1. So 3 minus 2x minus x squared. Yeah, this. Okay, so we've got, this is the square root of 3 minus 2x minus x squared. Okay, so sine theta, well, we already have sine theta. It's x plus 1 divided by 2. And so what is cosine theta? Adjacent over hypotenuse, so 3. Okay, and then theta is equal to inverse sine. Okay, so we've got and then sine theta cosine theta is x plus 1 times the square root of 3 minus 2x minus x squared divided by 4. So we're going to remove the 2 and put and that is the integral. Okay, so we look for potential substitution. If we said u is equal to 4x plus 1, that wouldn't work. Well, you know, it might work. And I say it might work because, so if u is equal to 4x plus 1, then du is equal to 4 dx. And so, you know, this 4 dx, like we have a constant dx, that occurs on the outside here, but I'm not sure. So 4x is equal to u minus 1. X is equal to u minus 1 divided by 4. So x squared is equal to u minus 1 squared divided by 16. But yeah, we're still going to be left with a u to the 1/2 power in the denominator, so that's not going to work. Okay, so whenever I see any radical with a function of x inside, you know, if I see like a squared plus or minus x squared plus or minus a squared, I think trig substitution, but we don't have that here. And so, you know, in particular with a square root, but if I see any radical, like a cube root, fifth root, whatever, with a function of x inside, there's always the option of saying that u is equal to that entire radical expression. And so we do this, in particular, we do this when we're trying to turn like a fraction like this into a rational expression. But you could do this in general, even if you don't have a fraction, because, okay, because if it's not a fraction, but you're still turning it into like a polynomial. So, okay, so when we're rationalizing, a lot of times we'll square both sides here to make it easier to get to differentiate, to get a cleaner du dx. However, when I see the 1 over 4x plus 1, I'm thinking, let's go ahead and do Okay, times the derivative of 4x plus 1 is 4. So we've got okay, so we've got 1/2 du is equal to right, and that occurs here. 1 over the square root of 4x plus 1 dx is here. So, okay, but we're also going to need an x squared, so square both sides of this, and then we solve for x. So u squared minus 4x is equal to u squared minus 1, so u squared minus 1 divided by 4. X squared is u squared minus 1 squared. Okay. So now we've got 1 over x squared, so okay, times, and then just 1/2 du. Okay, so we've got there we go. And so, we can solve this. It might be difficult, not difficult, it's going to take a little time, but we can solve it. We can integrate any rational function. Okay, so we said that u was equal to the square root of 4x plus 1, and this resulted in this integral. Okay, so now we just need to integrate this rational function. Step 1 for integrating a rational function, check to see if the order of the numerator is less than the order of the denominator. It is. Next step, fully factor the denominator. So let's do that. All right, we do have a quadratic factor squared. And so, that's, again, when we're factoring a polynomial, we're trying to break it down into, we know we can break down any polynomial, we can factor it into strictly products of linear and quadratic factors, either those factors to the first or any positive integer power. So potentially this is already factored. However, we look at the quadratic and we see that this can be factored further. So we can do u plus 1 times u minus 1 okay, and then let me do this. So we can, with properties of exponents, we can bring the 2 that's squared like this. Okay, so now it's fully factored. So now let's write the form of the decomposition. We've got 2 linear factors, both squared. Okay, so we have u plus a over u plus 1, and then u plus 1 squared, and then b in the numerator, and u minus 1. Okay, so now let's solve for A, B, C, and D. Multiply this entire equation by the least common denominator to clear the fractions. So we've got okay, so now if we let u equal 1, then all of these go away except for this one. U plus 1 is 2. 2 squared is 4, so 4. D is equal to 1/4. Okay, if we let u equal -1, then, so we've got 1 equals, all of these go away except for this one. -1 is -2. -2 squared is 4. 1 is equal to 4b. So b is equal to 1/4. Okay, if we let u equal 0, we get, so 0 plus 1 is 1, 0 minus 1 is minus 1 squared, so just a. Here, 0 minus 1 squared is 1 times b, so just plus 1/4. 0 plus, okay, 1, c, so minus c. And then 1 squared times d, okay, plus 1/4. So we've got a minus c plus 1/2 is equal to 1. A minus c is equal to 1/2. And so multiplying this entire equation by 2, you've got 2a minus 2c is equal to 1. Okay, now if we let u equal 2, then we've got, so 3 times 1 squared, so 3a. Okay, 3 minus 1, so, or no, 2 minus 1, 1 squared, so just b, so plus 1/4. 2 plus 1, so 3 squared is 9 times 1, 9c, so plus 9c, and then plus 9d, so plus 9/4. So we've got 3a plus 9c plus 10/4, which is 5/2, is equal to 1, which is 2/2. 2/2 minus 5/2 is minus 3/2. So now multiply this entire equation by 2, and you get 6a plus 18c is equal to minus 3. Okay, so we've got these two equations and two unknowns. So if we multiply this equation by 3, we get 6a minus 6c is equal to 3. Okay, then we've got 6a plus 18c is equal to minus 3. Now let's subtract these two equations. Minus 6 minus 18 is minus 24. 3 plus 3 is 6. So c is minus 6 divided by 24 minus 1/4. Okay, so we've got 2a then minus 2c, so plus 1/4 is equal to 1. 2a is equal to 1 minus 1/4 is 3/4. 3/4, or no, wait. So 2a minus 2c, so it's going to be plus 1/2. 2 times, yeah. Okay, so 2a, 1 minus 1/2. So a is equal to 1/2 divided by 2 is 1/4. Okay, so we've got, so 1/4, and then b is 1/4, and then c is minus 1/4. And then d is 1/4. Okay, so what we've got is, the integral is, well, actually, okay, we want to, this is the decomposition of the rational function, but we want to distribute the 8 to each of these, right? So we've got, okay, so when it comes to, when we do the partial fraction, any of the decomposed pieces that in the denominator is any kind of linear factor to the first power, second power, whatever, you can solve all of those by just doing a substitution on that linear factor. Or if it's simple enough, you could just do it visually. Like here, we can just say, okay, so we've got 2 natural log of the absolute value of u plus 1, right? And then here, it would be, so if we say that z is equal to u plus 1, dz is equal to du. So this, you get 1 over z squared dz. And this integral then is minus 1 over z. So then z, okay, so what we have here is, this is going to be minus, and then u like that, minus 2 natural log of the absolute value of u minus 1, and then minus 2 minus, it would be like that. Okay, now, so we can simplify this. We got 2 natural log, we can combine the 2 logarithms. Okay, and then, so here, let's do this. So we factor out a 2, then we've got u plus 1 plus 1 over u plus 1 plus 1 over u minus 1. Let's combine these 2 fractions, because should make it cleaner when it comes to when we substitute back the u here. So 1 over u plus 1 plus 1 over u minus 1. If we make the common denominator, we've got, so we'll have in the numerator, we're going to have u minus 1 plus u plus 1, right? which is minus 1 plus 1 is 0, which is just 2u. Okay, and then in the denominator, we had this. Okay, and then so if we multiply the minus 2, we get, it's going to be minus 4u over that. So we've got okay, and so that's it. However, we need to put this in terms of x, and we said so we're going to substitute the x term back in for u. So we've got 2 natural log of, so u plus 1 okay, minus, okay, and yeah, this is why if we multiply the square root of 4x plus 1 times the square root of 4x plus 1 minus 1, it's going to be really simplified. So let's do that here. Okay, so the square root of 4x plus 1 times the square root of 4x plus 1 is 4x plus 1 minus the square root of 4x plus 1 plus the square root of 4x plus 1. It goes to 0, and then minus 1. So it's just 4x. So we've got in the numerator 4 but then the 4's cancel, so it's just the square root of 4x plus 1 over x. Plus c. And that is the integral. Okay, so I see we have a sine t dt or a cosine t dt, and the derivative of sine is cosine, derivative of cosine is minus sine. So I'm thinking, like a substitution, but with this t kind of complicates that. So maybe integration by parts. Oh, okay, no. If we come to the trig identities, we've got sine 2 theta is equal to 2 sine theta cosine theta. So if we do this, if we say 1/2 okay, so we haven't changed the integral, right? This is equal to right? And that's easier to work with. We can do integration by parts here. So, okay, so we're going to say both of these are easy, t and sine 2t are easy to differentiate and integrate. So let's then choose u is equal to t. We'd rather that. And so dv is equal to sine 2t dt. So du is equal to dt. V is equal to, so it's going to be minus 1/2 cosine 2t. All right, and we'll go ahead and include the one, we'll do the whole integral here. So, well, I don't want to make it confusing. Let's just try not to forget. So we're just going to evaluate the integral without the 1/2 out front. So t sine 2t dt is equal to u times v minus the integral of v du. So plus, bring out the minus, You know, and I think the textbook talked about how when you've got products of like power terms like this or polynomials and, you know, functions like sine, cosine, trigonometric, or logarithms, exponentials, those lend themselves to integration by parts because the polynomials continue to get reduced, right? We've eliminated the t here. Okay, so, but again, you don't have to, integration by parts, you could do it with absolutely anything. It doesn't have to have there's no restrictions. They talked about how it's common to, when you have a power, like a power term, t to the first t, you know, x to whatever, or a polynomial multiplying it, they call it a transcendental function like sine, logarithm, exponential. Okay, but so 1/2 t cosine 2t, integral of cosine 2t is 1/2 sine 2t. And there we go. So now we want to put the multiply the 1/2 out front, right? So we've got minus 1/4 Okay, can we simplify this any further? No, it doesn't look like we can. So that's the integral. Okay, so here, this is a rational function, right? You have a polynomial in the numerator, polynomial in the denominator. And so we're going to just do partial fraction decomposition to solve this, right? Well, then let's do the partial fraction decomposition process. Step 1 is you check to see if the order of the numerator is less than the order of the denominator. It is. Okay, then you fully factor the denominator, and it's fully factored. We've got a single linear factor squared, so we decompose that this way. Okay, now let's solve for a and b. Multiply by the least common denominator to clear the fractions. So we've got x is equal to okay, so if x is equal to minus 1, then b is equal to minus 1. So we've got, if x is equal to 0, then you've got a minus 1 is equal to 0, so a is equal to 1. So we've got a is equal to 1, and then b is equal to minus 1. Okay, so we can write this integral as, so we've got into two separate integrals. Okay, so we've got natural log of the absolute value of x plus 1 evaluated from 1 to 2 minus, and then we could do a u substitution here, but we can see that's going to be minus 1 over x plus 1, so evaluated from 1 to 2. Okay, so we've got natural log of the absolute value of 2 plus 1 minus natural log of the absolute value of 1 plus 1 plus 1 over 2 plus 1 minus 1 over 1 plus 1. All right, 1/3 minus 1/2 is what? So 2 over 2 times 1/3 is 2 over 6. 3 over 3 times 1/2 is 3 over 6. So minus 1/6. We've got natural log of 3 minus natural log of 2 minus 1/6. And we can combine those logarithms and get natural log of 3/2 minus 1/6. Okay, here I see this root x, and I think, you know, rationalizing, if we say that u is equal to root x, we could just turn this into strictly powers. Okay, so now we don't want to take the derivative here because we don't have a root x in the denominator. So let's square both sides. Now take the derivative of the entire equation with respect to x. So 2u du dx is equal to 1. So 2u du is equal to dx. Okay, can we need x cubed. Can we get x cubed? So u squared is equal to x. X cubed is equal to u to the 6th. Okay, so 1 plus u to the 6th, root x is u, and then du, or dx, is 2u du. So okay. So now let's solve this, and we see here, we can say that z is equal to u cubed. Therefore, dz is equal to 3u squared du. Therefore, 1/3 dz is equal to u squared du. And so what we've got is, so u squared du, let's take out that 1/3. So u to the 6th is z squared. And then there we go. Now this is that form, the variable squared plus constant, and so this is arctangent of z. Right? If we look here, see, arctangent of z. Okay, but z is equal to u cubed. But u is equal to root x. So x to the 1/2 cubed is x to the 3/2. So there we go. Okay, so looking at this, what I notice is that, so we can make a substitution that u is equal to e to the x, and that would potentially work because we can rewrite the integrand as e to the x times e to the x. Right? If you combine these, you get x plus e to the x. So now if we say that u is equal to e to the x, then du is equal to e to the x dx. And so what we've got is e to the u du. which is e to the u, but u is e to the x. Okay, so how do we do this? Obviously, how in the world do we deal with this absolute value? Well, you shouldn't get intimidated by absolute values. You just need to slow down and think about it. Okay? When it comes to the absolute value, this is what you always need to keep in mind when you see an absolute value. You can remove the absolute value if you know where you're at in the x domain. That's the idea. If you're in the negative x domain, you can remove the absolute value by putting a minus sign in front. If you're in the positive x domain, you just remove the absolute value. Okay, so what we can do then is we can separate this into two separate integrals. We can say that we're going from minus 3 to 0. In that case, we're integrating in the negative x region. Think about it. What is the meaning of a definite integral? We've got some function, and we're getting the area under it. Well, if we're where we're at along the x on the function is defined by the limits of integration. So if we're going from minus 3 to 0, then we're in the negative region. So we know, so we can remove, we can do this. Why is that? Because how do you remove absolute values? How do you simplify absolute values? If you know x is negative, if I have the absolute value of x and I know that the input's going to be negative, well then this is going to be negative x, because when I put the negative in, the negatives cancel and it becomes positive. Okay, and then we're going to go plus 0 to 3, and then in the positive region, you just remove the absolute value. And that's it. Okay, now to solve these, we've got these two rational functions. The orders of the numerator and denominator are the same, so we would do polynomial long division, but let's just go ahead and make the substitution. So here we'll do u is equal to 1 minus x, so du is minus dx. And so what we've got is, okay, so when x is equal to minus 3, you got 1 plus 3, u is equal to 4. When x is equal to 0, u is equal to 1. Okay, now x is equal to 1 minus u. Okay, and then we have a minus sign out front, du. So all this substitution does is it flips the numerator and denominator, and this is more, we can integrate this, right, with this single u in the denominator. Because why? Because we can say, right, so we've got minus natural log of the absolute value of u minus u, going from 4 to 1. So we've got minus natural log of 1 is 0 minus 1. Okay, so minus 1 minus, and then natural log of 4 is 2 natural log of 2 minus 4. So this is minus 1 minus 2 natural log of 2 plus 4. So 3 minus 2 natural log of 2. So distribute the minus, and you got 2 natural log of 2 minus 3. Okay. So now here, if we say u is equal to 1 plus x, So du is equal to dx. When x is equal to 0, u is equal to 1. When x is equal to 3, u is equal to 4. Okay, x is equal to u minus 1. So we've got u minus natural log of the absolute value of u. Evaluate this from 1 to 4. So we've got 4 minus the natural log of 4 is 2 natural log of 2 minus 1 minus natural log of 1 is 0. So 3 minus 2 natural log of 2. We want to add these up. So we've got 2 natural log of 2 minus 3 plus 3 minus 2 natural log of 2, which is 0. So this is equal to 0. Okay, so we can see that this is okay, so we've got a rational function here. And so we can definitely solve this, but you know, this could potentially take a while. So let's see if we can do something to simplify this. Let's say that u is equal to x minus 1. Therefore, du is equal to dx. And so in that case, we've got u to the 4th, and then u minus 1 cubed du. And to me, this is better because we've got this u to the 4th in the denominator. It's easier, we can split this up into separate integrals. So to me, let's go ahead and distribute this u minus 1 cubed. So u minus 1 squared is u squared minus 2u plus 1 right? So this is a lot, you know, this seems messy, but we can separate up into separate integrals. Okay, so u cubed minus 2u squared plus u minus u squared plus 2u minus 1. So this is u cubed minus 3u squared plus 3u minus 1. So and that's over u to the 4th. Okay, and so what we have is now separated up into separate integrals, 1 over u du minus, and then take out the 3 yeah, this is going to work great. Okay, so we've got natural log of the absolute value of u minus, and then this is going to be minus 1 over u, so plus 3 over u. Now, the integral of 1 over u cubed, we can think about the power rule for integration. So u to the minus 3, we do u to the minus 3 plus 1 over that same value. Okay, and so that's going to be minus 3 over 2u squared. Okay, and then here we're going to have, so u to the minus 4 plus 1, minus 3 over minus 3. So we're going to have plus 1 over 3u cubed plus c. All right, so now let's just substitute the u is equal to x minus 1. So natural log of the absolute value of x minus 1 plus and there we go. Okay, and I made a mistake here. We've got u to the 4th, but then this is going to be u plus 1 cubed, right? Add 1 to both sides, and so, okay, you've got u squared plus 2u plus 1, and then you end up with u cubed. So, okay, u cubed plus 2u squared plus u plus u squared plus 2u plus 1. U cubed plus 3u squared plus 3u plus 1. So this is a plus here. So this is plus, this is plus. So this is minus and minus. These two are minuses. There we go. Okay, so looking at this, I'm thinking, say that u is equal to the square root of 4x plus 1, because that rationalizing idea, we can get rid of the radical, but then also because if we take this derivative from this point, we get this root 4x plus 1 in the denominator, in the differential, which is, and that's what it is in the integrand. So, okay, but then we've got times the derivative of 4x plus 1, so, right? So, okay, now we've got the 4 and the 2 cancel. So it's 1/2 du is equal to okay. Now we're going to need x, so u squared is 4x plus 1. 4x is equal to u squared minus 1. X is equal to u squared minus 1 divided by 4. Okay, so now let's make the substitution. 1 over x is 4 over u squared minus 1. And then 1 over the square root of 4x plus 1 dx is 1/2 du. So we've got okay. So here we want to, let's decompose this. So we've got u plus 1. Okay, so one is equal to so when u is equal to 1, b is equal to 1/2. When u is equal to minus 1, a is equal to minus 1/2. So, okay, so now you multiply by 2, you just get okay, so minus natural log of the absolute value of u plus 1 plus natural log of the absolute value of u minus 1. This is natural log of the absolute value of u minus 1 over u plus 1. But u is the square root of 4x plus 1. Okay, there we go. All right, so here, another method you can use when you're trying to figure out how to solve an integral is just algebraic manipulation. And so we can multiply this by something or whatever, and just because it makes it more complicated isn't necessarily a bad thing. So I think about, so 1 minus sine x, I think about conjugates, right? So like 1 plus sine x is the conjugate. So let's do this. So over 1, and let's multiply this by one in the form of the square root of the conjugate. Okay. So we've got 1 minus sine x times 1 plus sine x is 1 plus sine x minus sine squared x, which is great because we know that's going to be cosine squared of x. And then we still have this, which is not so great. Okay, so we know 1 minus sine squared x is cosine squared x. And so we've got okay, and so this integral is equal to, yeah, this is good. Why is this good? What do you see here? We can say that u is equal to 1 plus sine x. And therefore, du is cosine x dx. So we've got square root of u. So this is okay, power rule of integration. We get u to the minus 1/2 plus 1 over 1/2 plus 1. So 2. And so we've got 2 plus c. Okay. So I see a radical. Well, okay, they talk about, we talked about how with radicals you can substitute radicals to rationalize, right? But then there's this 1 here, so let's do this. U is equal to 1 plus square root of x. Let's just start there. Okay, now I'm not going to take the derivative yet because the 1 over 2 root x isn't going to help us. So let's do u squared is equal to, well, this might not work either, 1 plus 2 root x plus x. That's not going to help us. So, okay, let's do u is equal to root x and see what happens. u is equal to root x. So u squared is equal to x. Take the derivative with respect to x of the entire equation. So 2u so we've got 2u du is equal to dx. Okay, so we've got 1 plus u to the 8th times 2u du. So let's bring out a 2, and then u okay, now, all right, when x is equal to 0, u is equal to 0. When x is equal to 1, u is equal to 1. So, okay, I like this. To me, this is easier to work with than this. We've gotten rid of that root. All right, so let's try this. Now, if we said z is equal to 1 plus u, then dz is equal to du, and the purpose of this is that we're going to get rid of this 1 plus u, we're going to get rid of this expression to the 8th power. So we've got, and so, okay, u is equal to z minus 1. That's okay, because we don't have that to the 8th power. And then z to the 8th. dz. Okay, when z is equal to, no, when u is equal to 0, z is equal to 1. When u is equal to 1, z is equal to 2. Okay, so we're getting somewhere here. Because now we can say we've got z to the 9th minus z to the 8th dz. So what we have is 1/10 z to the 10th minus 1/9 z to the 9th, evaluated from 1 to 2. So we've got 1/10 2 to the 10th. So 2 to the 10th over 10 minus 2 to the 9th over 9, and then minus 1/10 minus 1/9. So okay, so we've got 2 to the 11th over 10 minus 2 to the 10th over 9 minus 1/5 plus 2/9. Okay, so 2 to the 11th divided by 10, 2 to the 10th divided by 9. So this minus this minus 1/5 plus 2/9. 4097 over 45. Okay, so trigonometric integral. And so just looking at this, I want to try and use the, not trig identities, but just see if we can put this into another form with just sines and cosines, just tangents and secants, or just cotangents and cosecants. So let's see what we have. Sine theta, and then secant is cosine, so maybe cosine theta, and then cotangent is cosine theta over sine theta. Yeah. Okay, so is that right? So 1 over secant is cosine. Cotangent is cosine over sine. Yeah. So this is cosine squared theta. Okay, now we know how to solve just a cosine or sine to an even power by itself. We use the half angle identity. And so that's cosine squared theta is equal to 1/2 plus cosine 2 theta. So bring out the 1/2. Okay, so we've got, and we've got theta plus 1/2 sine 2 theta, right? And we want to evaluate this from pi over 6 to pi over 3. So we've got pi over 3 plus 1/2 sine of 2 pi over 3. So sine of 2 pi over 3 is root 3 over 2. So root 3 over 4. Okay, minus, and then pi over 6 plus 1/2 sine of 2 pi over 6, so 1/2 sine of pi over 3. So sine of pi over 3 is root 3 over 2 as well. 1/2. Okay, so root 3. So we've got 1/2 times pi over 3 minus pi over 6. So that's 1/2 times 2 pi over 6 minus pi over 6. 1/2 times pi over 6. Pi over 12. Okay, so looking at this, what comes to mind is in the integration by parts section, we found the integral of the natural log of x using integration by parts. And so the only thing I can see here is, I can't see any other, there's no trig properties or trig identities with inverse trig functions. Let's try and use integration by parts to get this. Okay, so the u is going to have to be inverse sine squared, because we can't make that the dv, because that's what we're trying to find the integral of. Okay, so then dv is going to be equal to dx. Okay, and so if we look at our the table for the derivatives of inverse trig functions. The derivative of inverse sine is 1 over the square root of 1 minus x squared. Okay, so chain rule, we've got 2 times inverse sine of x times the derivative of inverse sine of x, which is 1 over the square root of 1 minus x squared. So we've got 2 inverse sine x like that. So du, okay, and then v is equal to x. All right, so u times v minus the integral of v du. So take out the 2. This looks complicated, so I'm not sure if this is going to work. Looks like we're making it more complicated. Okay, well, actually, this x is not so bad, because if we substitute 1 minus x squared, we get like an x dx. So in that case, let's do integration by parts again. So just on the integral, and we can't forget about the 2. So we're going to say that u is equal to inverse sine of x, and then we've also taken down the power of we don't have inverse sine of x squared anymore. And then okay, well, no, we don't want to do u. We don't want to get confused. So we'll say z is equal to, and then dp is equal to, because we can integrate this with the substitution. So dz is okay, and then let's integrate this. So the integral we'll make another substitution. So let's use m. We'll say m is equal to 1 minus x squared. Therefore, dm is equal to minus 2x dx. So minus 1/2 dm is equal to x dx. So we've got, take out the minus 1/2. We've got okay, so minus 1/2 so m to the minus 1/2 plus 1, and then minus 1/2 out front. So we've got minus root m and m is equal to 1 minus x squared. So there we go. So P is equal to, okay, so we've got Okay, so u times v, in that case, that's this and this. So minus the integral of, and that would be v du. And yeah, look, okay, so these are going to cancel. Yeah, this is going to work. Bring out the minus, and then this goes to dx, which is just x. All right, cool. So we got x minus okay. So plus c. Oh, and there's a 2 here, right? I didn't distribute the 2. Yeah. Okay, so this looks to me just like integrating a rational function. There's a standard rational function integral. So step 1 is we check to see is the order of the numerator less than the order of the denominator. In this case, it is. It's 2. The numerator order is 2. Denominator order is 3. So rational function, a ratio of polynomials, right? These are 2 polynomials. Okay, so the next step then is to fully factor the denominator. Okay, so when it comes to factoring, if we've got 4 terms, we think about grouping. So let's bring these terms, let's rearrange it like this. Now here we'll factor out an x, and then, okay, so and then we factor out an x squared plus 1, so there we go. Okay, so that's fully factored. The denominator is fully factored. We can't go any further. We've got a quadratic factor to the first power and a linear factor to the first power. So let's write the form of the decomposition. Let's do the linear factor first. Okay, now the quadratic factor to the first power like that. Okay, now we need to solve for a, b, and c. Let's multiply by the least common denominator to clear the fractions. So we've got 3x squared plus 1 is equal to okay, so now if x is equal to minus 1, we've got 3 plus 1 is equal to 2a. 2a is equal to 4, so a is equal to 2. Okay, if x is equal to 0, we've got 1 is equal to 1 times a, so 2 plus, and then just c. 2 plus c is equal to 1, so c is equal to minus 1. Okay, if x is equal to 1, we've got 4, and then 2a, so 4 plus b minus 1 times 2. So 2 plus 2b is equal to 4. 2b is equal to 2. b is equal to 2. Or b is equal to 1. b is equal to 1. Okay, so we've got a is equal to 2. And then we'll have x minus 1 over here. Okay, so we've got all right, now to solve this, we talked about in this section for integrating rational equations, we separate this into two separate integrals. So okay, so here we've got, so 2 times natural log of the absolute value of x plus 1 evaluated from 0 to 1. And so this is natural log of 2 minus natural log of 1. Natural log of 1 is 0, so this is just natural log of 2. So this is 2 natural log of 2. Okay, now this here, we can come off to the side. We use a substitution. We say u is equal to x squared plus 1. So du is 2x dx. 1/2 du is x dx. So we've got, bring out the 1/2, 1 over u du. When x is equal to 0, u is equal to 1. When x is equal to 1, u is equal to 2. So 1/2 natural log of the absolute value of u evaluated from 1 to 2. So this is going to be 1/2 natural log of 2 minus natural log of 1, 1/2 natural log of 2. Okay, so plus 1/2 natural log of 2. 2 natural log of 2 plus 1/2 natural log of 2 is 2.5 natural log of 2. 2.5 is 5/2. So okay. Now this, we referenced the formula. Okay, so a is 1. So 1 over 1, and we've got, so inverse tangent of x evaluated from 0 to 1. Okay, inverse tangent of 1 is pi over 4. Okay, so we've got and then inverse tangent of 0 is 0. So that is it. We've just got and that's it. That's the integral. Okay, so here's a trigonometric function, and it's not in that standard form like a product of a sine power and a cosine power, but we could still probably make this work with the same concepts, in the sense that, because what we do is we say that this is equal to sine squared x over cosine x sine x dx. Yeah, this is going to work. Okay, so what is this? What is sine squared x? 1 minus cosine squared x okay, and so now what we do is we say that u is equal to cosine x, and therefore du is minus sine x dx. So we've got 1 minus u squared, okay, and then bring out the minus sign, du, and there we go. So this is okay, so we've got plus, okay, so we've got 1/2 u squared minus the natural log of the absolute value of u. So this is 1/2 cosine squared x minus natural log of the absolute value of cosine x plus c. Okay, so this is a trigonometric integral. We've got a product of a power of a sine and a power of a cosine. And so what we want to do is we want to take out one of these sines or one of these cosines and pair it with the dt. But which one do we take out? We're going to take out a sine from the odd power because then we can, with an even power of sine, we can use sine squared t plus cosine squared t is equal to 1 to transform this into a function purely of cosine. Okay, so we've got 2 sine squared t's. So 1 minus cosine squared t, 1 minus cosine squared t, cosine to the 4th of t, sine t dt. And so now we can say that u is equal to cosine t, therefore du is minus sine t dt. So minus du is equal to sine t dt. And so what we have is u to the 4th, 1 minus u squared, 1 minus u squared. Bring the minus sign out. And then du. Okay, so we've got u to the 4th and then 1 minus u squared minus u squared Okay, so we've got u to the 4th minus 2u to the 6th plus u to the 8th du. Okay, so we've got minus plus 2 minus. Okay, so we've got minus 1/5 u to the 5th plus 2/7 u to the 7th minus 1/9 u to the 9th plus c. So let's bring the positive to the front. Well, let's bring the 9th power to the front. So minus 1/9 cosine to the 9th of t plus 2/7 cosine to the 7th of t minus 1/5 cosine to the 5th of t plus c. Okay, so this is a trigonometric integral, and it's a trigonometric integral because the integrand contains all trig functions. But you know, the definition of a trig integral, it doesn't. They never gave an official definition. You know, to me, a trigonometric integral is any integral that you solve using the concepts, the techniques, the tricks that we used in the trigonometric integral section. You know, because even this here, this contains only trig functions, but we never solved, like we only looked at in that section, we looked at products of powers of sines, cosines, tangents, and secants, cosecants, and cotangents. But the purpose of that was to illustrate the tricks, the concepts, the techniques to approach any, you know, trigonometric integral or integral that involves trig functions. And so that's what we're going to do here. And so, okay, I see the sine of 2 theta, and I think that sine 2 theta is equal to 2 sine theta cosine theta. But usually with integration, you'd rather have the sine of 2 theta, but I feel like we might want to separate it because we're going to need to simplify this. We're going to need, you know, we're going to need to work with the basic trig function. So yeah, let's go ahead and do that. So sine 2 theta is 2 sine theta cosine theta. So let's bring out the 1/2. Okay, so the main trick that we learned about trig integrals is, so, you know, we want to have like a cosine theta d theta, or a sine theta d theta, or a secant squared theta d theta, or a secant theta tangent theta d theta, etc. So then we can substitute the corresponding trig function. Okay, and so, you know, this square root of tangent theta, the square root is problematic. However, if it's not problematic if we're going to end up in the end making the substitution that u is equal to tangent theta, then it's not problematic. And if we're going to do that, du is going to be secant squared theta. So let's see if we can create a secant squared theta d theta. Okay, so secant is 1 over cosine, so we've got this cosine here. And so let's multiply by 1 in the form of cosine theta over cosine theta. Okay, because in that case we will get a secant squared theta, right? 1 over cosine squared theta. So, well, wait up. Okay, so we've got 1/2 all right, so we would have a cosine theta and then okay, and then cosine 1 over cosine squared theta, and then secant squared theta d theta. Okay. And then so, okay, yeah. Cosine theta over sine theta is cotangent theta, but then 1 over cotangent theta is tangent theta, so yeah, here we go, perfect. Okay, and so we've got okay, tangent to the 1/2 divided by tangent to the first is 1 over tangent to the 1/2. And there we go. That's it. Now this root tangent is not problematic because what we do is we say u is equal to tangent theta. du is secant squared theta d theta. The idea is, okay, in this situation, we want to get just a function of tangent, no matter what it is, and then what's left over is secant squared theta d theta. Okay, and so we've got 1/2. All right, when tangent is equal to pi over 4, u is equal to, so tangent (1). Okay, when tangent is equal to pi over 3, u is equal to root 3. Okay, then we've got 1 over root u du. Okay, so u to the minus 1/2, the integral, u to the minus 1/2 plus 1 is u to the 1/2 over 1/2. So this was 2 over 2, so we just have root u. Root u evaluated from 1 to root 3. So the square root of 3 is the 4th root of 3 minus the square root of 1. And there we go. Okay, I see this 1 squared minus x squared, I think potential trig substitution. Regardless of but the square root makes it even more enticing. When I see the square root of a squared plus or minus x squared plus or minus a squared, then you really think trig substitution. But you know, as we talked about in this section, the square root isn't necessary. It's all about the a squared plus or minus x squared plus or minus a squared. Okay, now, however, we would rather not do a trig substitution if we can find a quicker way. But we can see if we said u is equal to 1 minus x squared, that's not going to really help us. So let's do the trig substitution. We've got this form, we have 1 minus x squared, this form. So we want to say x is equal to sine theta, 1 sine theta. X is equal to sine theta. Therefore, dx is equal to cosine theta d theta. And therefore, so 1 minus x squared is 1 minus sine squared theta, the square root of 1 minus sine squared theta, which is equal to the square root of cosine squared theta, which is equal to cosine theta. Okay, so we've got the making the substitution, the integral. Now we want to update the limits of integration, and so the way we do this is a little bit different with the trig substitution because it's the reverse of a regular substitution. So here we've got x is equal to 0. So solving for theta, inverse sine is 0. Okay, then we've got x is equal to root 2 over 2. So inverse sine of root 2 divided by 2 is pi over 4. Okay, so 1 minus the square root of 1 minus cosine squared theta is cosine theta. And then x squared is sine squared theta. Okay, but then dx is cosine theta d theta. So what we have is there we go. And we can solve any sine or cosine to an even by itself to an even power by using the half angle identities. So sine squared theta is 1/2. I believe it's 1 times 1 minus cosine 2 theta. Yeah. 1/2 times 1 minus cosine 2 theta. Okay, so 1 minus cosine 2 theta d theta. Okay, so we've got 1/2 and then theta minus 1/2 sine 2 theta. Evaluating this from 0 to pi over 4, not pi over 2. Okay. So we've got, all right, well, sine of 0 is going to be 0. And then this is, so all we're going to need to do is plug in pi over 4. So pi over 4 minus 1/2 sine of pi over 2. Sine of pi over 2 is 1. So pi over 4 minus 1/2 pi over 8 minus 1/4. Okay, so here, when I look at this, the first thing I notice is, well, okay, I think potential trig substitution. However, with the natural log of x, that's kind of scary, but still, that's something you could try. But then I noticed, so we have an x over the square root of x squared minus 1. That we could do if that was the integral by itself, if we took out the natural log of x, we could solve that using a u substitution. So to me, what we can do then, we can do integration by parts, because when doing integration by parts, we'd rather not have to integrate the natural log of x. We could. It's not the nicest integral, but we can get that integral. But we don't have to. We can the derivative of natural log of x is nice. And we can do integration by parts. We can say u is equal to the natural log of x. So du is 1 over x dx. And then we're left with dv is equal to right? Which is, looks messy, but this is actually not that bad of an integral, because we can say u, let's put it over here, u is equal to x squared minus 1, therefore du is 2x dx, so 1/2 du is equal to x dx. And so we've got the integral of u to the minus 1/2 du with a 1/2 out front. Is that right? 1 over root u, which is u to the minus 1/2. And the x dx is 1/2 du. Yeah. So you've got 1/2 and then the integral of u to the minus 1/2. So u to the minus 1/2 plus 1 is u to the 1/2 over 1/2. This is just root u. Okay? And so v is, right, because we plug in the u here. You see? So I feel like this still might not work, but let's just see. You know, that was, I guess to me, that was doable, right? You got this really, really complex integral, and the integration by parts is you know, not the derivative of natural log of x is easy, and this, you know, complicated looking integral is pretty easy. Okay, so u times v minus the integral of v du. So okay, and I would say that the integration by parts worked, because we have a simpler integral now to solve this entire integral. We've got a simpler integral. Unfortunately, it doesn't look like it's the you know, it's not just so straightforward, but it's definitely simpler. Okay, and so looking at this, I think I see the x squared minus a squared, x squared minus 1 squared under and also under a square root. So let's do a trig substitution. Okay, we've got x squared minus a squared, x squared minus 1 squared. So we want to say that x is equal to 1 times secant theta. X is equal to secant theta. Okay, so we're trying to solve. Let's make some room here. We're trying to solve you know, this is, you know, it's easy to forget about the negative sign out front, so we're just trying to stay organized. We're trying to solve this, and we're going to say that x is equal to secant theta. Therefore, dx is equal to secant theta tangent theta d theta. Okay, so the square root of x squared minus 1 is secant squared theta, the square root of secant squared theta minus 1, which is equal to the square root of tangent squared theta, which is equal to tangent theta. Okay, so making the substitution, we've got secant theta in the denominator, tangent theta in the numerator, and then secant theta tangent theta d theta. Okay, so tangent squared theta d theta. What is the integral of tangent squared theta? What we can do is tangent squared theta is secant squared theta minus 1, right? And so the derivative of tangent theta is secant squared theta. So this is secant squared theta d theta minus the integral of d theta. And now we've got tangent theta minus theta. That's the integral, okay? So now we need to convert this back to x. Well, we're not going to need the triangle, because what we've got is tangent theta, or no, we are going to need the triangle. Okay, because we have x equal to secant theta. What is secant theta? That's 1 over cosine. Cosine is adjacent over hypotenuse. So x over 1 is hypotenuse over adjacent. Okay, so we have 1 squared minus z, or 1 squared plus z squared is equal to x squared. So the square root of x squared minus 1 is this side. And therefore, tangent theta is equal to opposite over adjacent. Okay, so we've got, and then theta is, there we go. Okay, so, all right. That is this here. Now we got to distribute that minus sign appropriately. So we've got minus okay, so now let's get our bearing straight here. Where are we? So this was determining this integral here, which we just replaced, and that was the main integration by parts, right? We set up the original integration by parts, to this integral, and we just solved that integral and put it in. So that's the answer. This is it. This is the integral. And actually what we could do to make this simpler, we could factor out a square root of x minus 1 and then get natural log of x minus 1. That's probably looks a little bit cleaner. Right, we factored out this square root of x squared minus 1 here. Okay, so thinking about a substitution, if we said we don't have, like, let's say this was x to the 4th, a substitution still wouldn't work because, yeah, we'd get something x cubed dx, but this isn't x cubed dx. This is in the power of the e. Okay, now we have like a power here, like a polynomial power here, and then like a transcendental function. So like the textbook talked about, these lend themselves to integration by parts, and so I guess to me, that's the last resort, integration by parts. But I just want to try. Let's see what happens when we do this. I'm just curious. So we've got e to the something. The derivative of e to the something is e to that something times the derivative of that something. Okay, so minus 3x squared e to the minus x cubed. So du okay, and so we've got dx is equal to all right, so let's just see what this does. So we've got, let's put the dx in first. 3x squared e to the minus x cubed, and then x to the 5th. Okay. Okay, but okay, well, let's do, okay, we got, this is, so 3x squared e to the minus x cubed is u, right? So we've got x to the fifth, bring the minus sign out front. E to the minus x cubed is u. So bring the could bring the 1/3 out. So you've got x cubed du. Okay, but what is x cubed? If we take the natural log of both sides of this, so natural log of u is equal to minus x cubed. So we've got x cubed is equal to minus natural log of u. Okay, so taking out that minus sign, you've got 1/3 integral of natural log of u du. Now, in the textbook, we integrated the natural log of x using integration by parts. So let's just go grab that integral. Okay, so if we look here, integral of the natural log of, okay, so we can see the integral of the natural log of x is x natural log of x minus x. So this is okay, and so what we've got is 1/3 u, and then natural log of u minus 1. Okay, so 1/3 e to the minus x cubed natural log of e to the minus x cubed minus 1. Okay, but okay, but natural log of e to the minus x cubed is just x cubed. And we can take out a minus, and so we've got x cubed plus 1. And there we go. That is the integral. And so this is a good example of, we could have used integration by parts, and that would have worked, but sometimes a u substitution might not be obvious. And, and it's not like, we didn't start off with some, we have u and then du is something that's right in the integral, but it still worked. And to me, that was a little bit easier than integration by parts would have been. Okay, so looking at this, I see this sine of 2x, which I know is 2 sine x cosine x. And what I like about that is we have an option for both a sine x dx or a cosine x dx. So let's bring out the 2, and we've got okay, and so what we're going to do is we can choose the we can say that u is equal to cosine x. Therefore, du is minus sine x dx. So minus du is equal to sine x dx. And there we go. So we're going to bring out the minus. And so we've got cosine x over 1 plus cosine of the fourth of x. So u to the fourth plus 1. And there we go. We have the integral of a rational function, which we can always solve. Okay, and so now here, what we want to do is we want to make the substitution that z is equal to u squared. Okay, therefore dz is equal to 2u du. Right? So 1/2 dz is equal to u du. So what we've got is z squared plus 1 dz. And then we take out the 1/2. Okay, so now okay, and so, all right. Okay, and so now we can solve. Okay, and so now this is one of the standard forms that we have in partial fraction decomposition, and we solve this just by referencing this formula. So we've got the variable squared plus 1 squared here. So this is minus and there we go. Okay, but z is equal to u squared. Okay, and u is equal to cosine x. And so that is the integral. Okay, so looking at this, my first instinct is to go ahead and expand this for two reasons. First, because when you expand it, you can separate it up into separate integrals. But then also, you know, we're going to have one of those is going to have like a sine squared x, and I'd rather have a sine squared x than just a sine x. Okay, so we've got x plus sine of x times x plus sine of x is x squared plus x sine of x plus x sine of x is 2x sine of x plus sine squared x. Okay, and so we can go ahead and separate this up, and I feel like that's what we should just go ahead and do. I don't see why we want to have change this to 1 minus cosine squared x. No, so, okay. Then plus 2 okay, and so the integral of x squared dx is 1/3 x cubed. The integral of sine squared x dx, we know how to solve this. We use the half angle identity. So bring out the 1/2, and then sine squared theta is 1/2 1 minus cosine 2 theta. So 1/2 times x minus 1/2 sine 2x, right? That's the integral of cosine 2x. And so 1/2 x minus 1/4 sine 2x. All right, now that just leaves the integral of this integral. And so let's go ahead and I'll put this in blue because I don't want to forget about the 2. So, okay, what is this integral? This is perfect for integration by parts. Both of these are easy to differentiate and integrate. And so if we have a choice, we'd rather differentiate x because then it just gets eliminated. So du is equal to dx. V is equal to minus cosine x. So, and again, we don't want to forget about the 2 out front. U times v minus the integral of v du. So bring out the minus. So this is okay, and so let's put the sine of x first. Sine of x minus x cosine x. Okay, so what we've got is 1/3 x cubed plus 2 sine of x minus 2x cosine of x plus 1/2 x minus 1/4 sine of 2x. And I'm not sure, we can't really simplify that anymore, plus c. Okay, so this is one of the easier ones, obviously. We could just say that u is equal to at to solve this, but if we could actually do this in our heads, because what is the derivative of cosine? Oh, actually no, this is not as easy. Okay, this isn't quite that easy because of the square root. Yeah, if it was just sine of at, we could do it in our heads, but the square root makes it a little more complicated. So we could do integration by parts, and that should work fine. But I'm just curious, when it comes to like rationalizing, they talk about substitute for the entire radical. What would that do here? This might not do anything. Okay, so we do u squared is equal to at. So dt, we've got 2u du dt is equal to a. So 2u du is equal to a dt. So 2u over a du is equal to dt. Therefore, what do we have? Sine of u times 2u over a du, which is, so 2 over a u sine of u du. So yeah, that worked, because now we can think about integrating this. Let's check again. So u is equal to square root of at, u squared is equal to at, 2u du dt is equal to a, 2u du is equal to a dt, 2u over a du is equal to dt. Okay, so we've got sine of u times 2u over a du. Yeah, okay. So now we can do integration by parts on this. We'll say u, well, okay, we need to do, we'll say z is equal to u, so dz is equal to du, and then we'll say dp is equal to sine u du, so p is equal to minus cosine u. Okay, and so the integral of u sine u du minus, or no, just z times p, so minus u cosine u, and then minus the integral of p dz. So bring out that minus. Okay, so we've got, or wait, yeah, that's it. So, okay, so this is 2 over a Okay, now what is u? U is the square root of at. So plus c. Okay, here I noticed that we have a 1 over x, and the derivative of 1 over x is minus 1 over x squared. So this should be really simple to just say that u is equal to, we'll say 3 over x. Therefore, du is minus 3 over x squared dx. So minus 1/3 du is equal to 1 over x squared dx. And so now we can make the substitution. So when x is equal to 1, u is equal to 3. When x is equal to 3, u is equal to 1. Okay. And then we've got e to the u. And then 1 over x squared dx is minus 1/3 du. There we go. So minus 1/3 times e to the u. So this is just going to be e to the first minus e cubed, right? And so we've got 1/3 e cubed minus 1/3 e, and that might be cleaner to do it like this. Yeah, there we go. Okay, so I see a x squared plus a squared, and then especially that it's under a square root. So this lends itself to trig substitution. So let's go ahead and do that. Well, okay, I was thinking actually do a u substitution, since if we said u is equal to x squared plus 1, you have du is equal to 2x dx, and we have an x here, but this is a 1 over x. So that's not an x dx, it's a 1 over x dx. So, all right, we've got x squared plus a squared, so we want to say that that's this form, so we want to say that x is equal to, so a is 1, x is equal to tangent theta. Therefore, dx is equal to secant squared theta d theta. And so x squared plus 1 then is tangent squared theta plus 1. Tangent squared theta plus 1 is secant squared theta. Okay, so we've got x is equal to tangent theta. Square root of x squared plus 1 is equal to secant theta. And then dx is secant squared theta d theta. So we've got secant theta over tangent theta d theta. So how do we solve this? Well, we have secant theta d theta. That doesn't, the derivative of tangent theta is secant squared theta. And so we just need to just play with this. And so let's write this out and see. Let's change this to sines and cosines. So secant is 1 over cosine theta, and then tangent is sine theta over cosine theta. So yeah, perfect. 1 over sine theta is, and this we can go to the table of integrals. Integral of cosecant is natural log of cosecant minus cotangent. Natural log of the absolute value. And there we go. So now we just need to convert this back to x. Okay, so we've got tangent theta is equal to x divided by 1. Opposite over adjacent. Tangent theta is equal to opposite over adjacent. Okay, so 1 squared plus x squared is equal to the hypotenuse squared. So this is the, okay, so we need cosecant theta. Cosecant is 1 over sine. Sine is opposite over hypotenuse, so we need hypotenuse over opposite. Cotangent theta is, so tangent is opposite over adjacent, so we need adjacent over opposite. And so when we subtract these two, we get and there we go. Well, we have the plus c as well. Okay, so if we said u is equal to cosine x, then du is equal to minus sine x dx. And so it's tempting to do that substitution, but then the x still becomes an issue. Let's see. I'm just curious on what this does. Sine over cosine is tangent. 1 over cosine squared is secant squared. It's kind of the same idea then. If we said u is equal to tangent x, then du is secant squared x dx. And then the integral then is u okay, when u is equal to 0, inverse tangent, or what is, okay, now let's see, this is, no, we just say tangent. When x is equal to 0, what is u equal to? 0. When x is equal to pi over 4, what is u equal to? 1. Okay. So I guess that works, because then we can integrate this potentially using integration by parts. So yeah, let's try it. Okay, so let's bring this over here. So we've got okay, so I'd rather not integrate arctangent of u, and so if we say that, okay, we're going to do z is equal to arctangent of u, and then dp is equal to u du. And so, okay, the derivative of arctangent, that's nice. We don't have a square root to deal with. 1 over 1 plus x squared. So dz okay, and then p. All right, so z times p and then this going from 0 to 1 minus p, the integral of p dz. Wait. This should be a u squared. Okay, so okay, and then we can integrate this, or this is u squared. We can integrate this, right? So we've got a rational function, but the order of the numerator is the same as the order of the denominator. So let's do polynomial long division, u squared plus 0u plus 0, and then u squared plus 0u plus 1. U squared divided by u squared is 1. Now we multiply these by the 1 by the divisor. U squared plus 0u plus 1. Subtract these two terms, you get minus 1. So is equal to 1 minus, and then 1 plus u squared, so u squared, and that makes sense because 1 you can write as u squared plus 1 over u squared plus 1, and then you combine those two, you get u squared over u squared plus 1. So what we've got is integral and this is going from 0. Okay, let's distribute this 1/2. So we've got minus 1/2 here, and then plus 1/2 here. Okay, so, all right, plugging in the 0. Okay, this all goes to 0 if you plug in 0, and then 1. What is arctangent of 1? Pi over 4. So 1/2 times pi over 4 is pi over 8. Okay, this going from 1 to 0 is just 1, so minus 1/2 plus 1/2 times, okay, so this is that form, we have a quadratic in the form of like a squared or x squared plus a squared over just a 1, a constant. So that's for the partial fraction decomposition integral section. We get one of 4 forms when we do the full decomposition. And this is one of those 4 forms where we use this formula. So this is going to be, with a is equal to 1, we're going to have arctangent of u. So this is arctangent of u evaluated from 0 to 1. And we just did that. Arctangent of u is pi over 4. So this is pi over 4 times 1/2 is pi over 8. So pi over 4 minus 1/2. Okay, so here's a problem where we see this as a rational function. Okay, so we can think potentially, let's do the integration process for rational functions. So we first check, is the order of the numerator less than the order of the denominator? It is. So then the next step would be we would fully factor the denominator to where it's just consists of quadratic and linear factors. But this is one of those cases we talked about where, yes, any polynomial technically from a math standpoint can be, no matter what it is, can be factored to strictly linear and quadratic factors. But when it comes to t to the 4th plus 2, we have to use, with the basic factoring methods that we learn in algebra, we can't factor this any further. So we're not getting into how to factor this further. And so as far as doing partial fraction decomposition, we can't solve this if we were strictly relying on having to do partial fraction decomposition. Okay, so does that mean we just give up and say we can't solve this? Well, no. What we do in a case like this is we look for a potential substitution. And so if we look here, we can say that u is equal to t squared. Okay, so therefore du is 2t dt. So 1/2 du is equal to t dt. Okay, now the trick here is that t to the 4th is u squared. So what we've got is, take out the 1/2, and then u squared plus 2. Okay, now this we can solve. This is, fully decomposed. We have a quadratic factor to the 1st power, and it's already in that u squared, at variable squared plus a constant form. So since this is to the 1st power, what we do is we come to this formula, and we see that a is equal to root 2. So we've got 1/2 times 1 over root 2 Okay, so 1 over 2 root 2, is that, if we rationalize that, what do we get? Root 2 over 4, so, that's not much simpler. I'm just going to leave it as 1 over 2 root 2. Okay, but what is u? U is t squared. And there we go. Okay, so e squared, what do we do here? This is kind of a trick question. What is e squared? There's no variable in that. That's just a number. E squared is a number. It's like saying, what is the integral of 4 dx? What is the integral of 4 dx? It's 4x, right? Well, plus c. So x e squared plus c. What is this derivative? What is the derivative of x times a number? It's just that number plus the derivative of c with respect to x is 0, so the derivative is e squared of this. Okay, so 1 over secant is cosine x, and I see a sine of x in there. So to me, we should just say u is equal to sine of x. Therefore, du is equal to cosine x dx, and this should work just fine. So we've got e to the u du, e to the sine of x plus c. And that's the integral. Okay, so here, if we just say u is equal to 3x plus 1, then du is equal to 3 dx. 1/3 du is equal to dx. And so what we've got is u to the root 2, take out the 1/3 du. And we can integrate that, no problem. Now let's update the limits of integration. When x is equal to 0, u is equal to 1. When x is equal to 1, u is equal to 4. Okay. So power rule of integration, we can apply that with any real number power. And so u, we've got, this is going to be u to the root 2 plus 1 over root 2 plus 1. Okay, and evaluating this from 1 to 4. So we can take out that root 2, 1 over root 2 plus 1. Okay, and we're left with okay. So we've got 4 to the root 2 plus 1 power minus 1 to the root 2 plus 1 power, so just minus 1. And so that's it. Okay, so here, I'm thinking about, in a previous problem, we saw that the derivative of arc tangent x is 1 over 1 plus x squared. And we have a 1 over 1 plus x squared in this integrand. So what we want to say is that u is equal to arc tangent x, and therefore du is, right? And so what we've got is square root of u du. All right, now when x is equal to 0, arc tangent x is equal to 0, I believe. Yeah, and then when x is equal to 1, pi over 4 maybe? Yeah. Okay. So we've got u to the 1/2. U to the 1/2 plus 1/2 is 3/2. So u to the 3/2 over 3/2. So 2/3 u to the 3/2 evaluated from 0 to pi over 4. So what we've got is 2/3 times, and it's just going to be pi over 4 to the 3/2. And then that's it. And actually what we could do is, so we've got 2/3 times 4 to the 3/2, 1 over 4 to the 3/2, times pi to the 3/2. Okay, square root of 4 is 2, and 2 cubed is 8. So we've got 2 cubed there we go. Okay. So we've got pi to the 3/2 divided by 12. All right, so I see this denominator, this ugly denominator, and when, I think about multiplying by the conjugate of this, because that helps with roots, and it'll also simplify the fraction, condense down the fraction, which is in the denominator, which is nice. It'll condense down the denominator. So what is so we want to multiply by 1 in the form of all right. So multiplying these two, root x plus 1 times root x plus 1 is x plus 1. All right. Minus root x times root x plus 1 plus root x times root x plus 1 is 0. And then minus root x times root x is minus x. So x minus x is 1. So yeah, I mean, this is multiplying by the conjugate is nice. And so what we're left with is which is simpler. So that's definitely what we wanted to do. Okay, and now what we can do is we can separate this into two separate integrals. Okay, and here we would usually do a u substitution, but it's the derivative of x plus 1 is just 1, so we can just think about it like, okay, the power rule of integration. So x plus 1 to the 3/2 over 3/2, and that's going to be the integral. And then here we have x to the 3/2 over 3/2. So 2/3 x plus 1 to the 3/2 minus 2/3 x to the 3/2. Okay, just looking at this, the first thing that comes to mind is trig identities, specifically. So the sine of 2 theta we know is 2 sine theta cosine theta. And let's see what else. So sine 2 theta is 2 sine theta cosine theta, and then cosine. So let's copy these. Okay, so to me, we can work with these two identities and get this into a better form. Well, actually, okay, isn't there... Don't we have something like, yeah, like this, right? Sine alpha, cosine beta. But that's not going to help us here because we don't have like plus cosine alpha, sine beta. Okay, so no. All right, so let's see. If we've got sine of 6x, if we say that u is equal to 3x, then we've got sine of 2u, which is equal to 2 sine u cosine u. Okay, so therefore, this is 2 sine 3x cosine 3x. Okay, so just looking at this, I see there's a cosine 3x here and a cosine 3x here. So if we take out the 2, then we've got sine 3x cosine squared 3x. Okay, and actually, okay, and so now we can work with this because we're going to say, because now we have the same argument. So we're going to say that u is equal to 3x, therefore du is equal to 3 dx, 1/3 du is equal to dx. So we've got, all right, when x is equal to 0, u is equal to 0. When x is equal to pi, u is equal to 3 pi. There we go. And we can solve this, right? And so actually, let's write it this way. We can solve this because we're going to say z is equal to cosine u, therefore dz is equal to minus sine u du, so minus dz is equal to sine u du. Okay, so this becomes, all right, when u is equal to 0, z is equal to 1. When u is equal to 3 pi, so cosine 3 pi, we can think that's going to be minus 1. Right, because cosine of pi is minus 1. Okay, and then bring out the minus sign, so z squared dz. And what's nice about a definite integral is that we're doing all these substitutions. We don't have to back substitute. We're just going to evaluate the definite integral because we're updating the limits of integration as we go. So minus 2, this is going to be, okay, we're going to have minus 2/3 z cubed evaluated from 1 to minus 1. Okay, so minus 1 minus 1. Four thirds. Okay, and I think I messed up somewhere. Let me look. Okay, did I do this right? U is equal to 2x. So, no, U is equal to 3x. All right, U is equal to 3x. So this is sine 2u, which is equal to 2 sine u cosine u. So that's right. Okay, U is 3x, du is 3dx, 1/3 du is equal to dx. Oh, wait, yeah, where's that? Where I left out this 1/3. So this is 2/3. So this is 4/9. Okay, here we definitely want to substitute u is equal to root x. Why is that? Well, because then we get this is equal to u, but then we know that du is 1 over 2 root x dx. And so we've got, we see we have 1 over root x dx in the integrand, right? 2 du is equal to 1 over root x dx. So we've got 2 to the u and then times 2 du. Okay, what is the integral of a exponential? Well, that's easy because you just say it's going to be, this will be 2 over natural log of 2 times 2 to the u. Like, okay, the integral of the derivative of 2 to the u power is 2 to the u natural log of 2. That's the derivative of exponentials. So if you think about the integral, it's going to be 2 to the u over natural log of 2. Because then because 2 to the u over natural log of 2, what is the derivative of that? Well, if you have 1 over natural log of 2, you can take that out as a constant, times 2 to the u. So 2 to the u, natural log of 2, then divided by natural log of 2, you're just left with 2 to the u. So this is 2 over natural log of 2, 2 to the u. Okay, but u is root x, so okay, so here we've got a rational function, and so what we do is we say, is the order of the numerator less than the order of the denominator? It is. So then we want to fully factor the denominator. Okay, so can we factor this x to the 6th plus 3x cubed plus 2? Well, if we say that u is equal to x cubed, then we've got u squared plus 3u plus 2, okay? And then so u 2, 1, u squared plus 3u plus 2, okay? But u is equal to x cubed. All right, so, you know, what we learned about factoring, we're not done yet because we have the sum of 2 cubes. And so the formula for the sum of 2 cubes is x cubed plus a cubed is x plus a x squared minus ax plus a squared. Okay, so we've got x cubed plus 2, then x plus 1, x squared minus x plus 1. Okay, now from the methods we learned, this is fully factored, right? We would, as far as factoring earlier in the algebra, in the beginning of the algebra playlist, we're done here, okay? But the issue is we can't do partial fraction decomposition on this. We have to have all strictly quadratic and linear factors. Okay, these are linear and quadratic, but this is not. Okay, and so this is one of those cases where, you know, again, every single polynomial can be, no matter what it is, you know, there's more advanced methods, but you can break it down into linear and quadratic factors strictly and then do partial fraction decomposition on it. But here's a case where we can't go any further. But I mean, we could figure this out, because if we said that, yeah, what we would do is we'd say this is cube root of 2 cubed. And so, yeah, so we would say this is x plus cube root of 2, then x squared minus cube root of 2x plus cube root of 4. And then so, okay, now we've fully factored it. So now we could do the partial fraction decomposition. Okay? But we're not going to do that. We're not going to do partial fraction decomposition on this. Right? Just pointing it out. We've got a linear factor here, and then you've got 2 quadratic factors here. But we're not going to do partial fraction decomposition. Let's just imagine that, for some cases we can't actually figure out how to. You have to have more math knowledge to actually figure out how to continue factoring. Like we talked about with x to the 4th plus 1. We don't have any. We don't have a formula for this that we learned in algebra to be able to expand this out. So we couldn't go any further here with our basic knowledge. So what do? Does that mean we can't, since we can't, let's say we couldn't get past this point, does that mean we can't solve this? Well, we can't solve it with partial fraction decomposition, but it doesn't mean it's unsolvable with the knowledge we have, because what we can do is we can look for a substitution. Okay, so what we're going to do is we're going to say, what if u is equal to x cubed? Then du is equal to 3x squared dx. 1/3 du is equal to x squared dx. Okay, and so this is going to work because what is x to the 6th? That's u squared plus 3x plus 2. And look, we've got x squared dx. So, and then bring out this 1/3. Okay, so now we can solve this because we've got a quadratic. So what do we do now? Well, we can want to factor this if we can. Can we factor this? Well, yeah. So we've got, this is, oh wait, this should be a u. Okay, so we've got u plus 2, u plus 1. Okay, so now we want to separate this up. So we can do partial fraction decomposition. Here, we've got 2 linear factors to the first power. Okay, so we've got 1 is equal to a. Okay, so when u is equal to -1, you've got just b. So b is equal to 1. When u is equal to -2, you've got, so a is equal to -1. So we've got -1 and 1. So, okay, we've got 1/3 or -1/3 plus 1/3. Okay, so -1/3 natural log of the absolute value of u plus 2 plus 1/3 natural log of the absolute value of u plus 1. Okay, this is 1/3 natural log of the absolute value of u plus 1 over u minus 1. But u is equal to x cubed, so x cubed plus 1, x cubed minus 1, and there we go. Or wait, no. This was over u plus 1 over u plus 2. So x cubed plus 2. Okay, so here, I'm not really sure. The first thing I'm thinking is, let's try this. Because, yeah, even though we're going to get, like, it's not like when we take this derivative, we get something that's contained in the integral, something dx, but this might help us to get rid of this fraction. So du is e to the x dx. So dx is equal to du over e to the x, which is equal to what? Which is equal to that. So we've got u in the denominator and then dx in the numerator. And so dx is that's going to work. So we've got u times u minus 1 is u squared. Well, no, we can just leave it like what we end up with is a rational function. So what we need to do is do partial fraction decomposition. So this is equal to u okay, so we've got 1 is equal to a. So when u is equal to 0, a is equal to minus 1. When u is equal to 1, b is equal to 1. Okay, so this is equal to minus minus natural log of the absolute value of u plus natural log of the absolute value of u minus 1, which is combining these two. Okay, now u is equal to 1 plus e to the x. So we've got the natural log of the absolute value of 1 plus e to the x over 1 plus e to the x minus 1, so just e to the x, plus c. And actually, we can simplify this because we've got natural log of the absolute value of 1 plus e to the x minus natural log of the absolute value of e to the x. Okay, but e to the x is always positive. So 1 plus e to the x is always positive. But this is x. So, and then wait a minute, hold up. I'm okay. why did I put natural log of u over u minus 1 here? So, okay. Let's come back to this point. So, now let's substitute. We've got natural log of the absolute value of u is 1 plus e to the x minus natural log of the absolute value of, of u minus 1. 1 plus e to the x minus 1, so this is just going to be e to the x. Minus natural log of the absolute value of 1 plus e to the x. Is that right? 1 plus e to the x minus 1 is just e to the x minus, yeah, okay. But e to the x is always positive for all x. So we could take away the absolute value on both of these. Okay, but natural log of e to the x is just x. So we've got and that is the more simplified form. Okay, so just looking at this, I don't have any gut feeling about what to do, except for, so if we said that u is equal to then we're going to end up with a constant over this. But I don't know how well that's going to work out, because we have the chain rule, and we're going to be integrating the square root of x plus 1 or differentiating the square root of x plus 1 as well. So I'd like to see what happens doing this. So du is, so the integral of the square root of something is 1 over 2 square root of that something times the derivative of that something. So what is the derivative of square root of x plus 1? That's just going to be 1 over 2 root x. So what we've got is right, because square root of x plus the derivative of 1 is 0. Okay. And dx. So what we've got is, let's see, 4 and then right, and so this is why I wanted to try this, because we've got this, which is the entire integrand. And so this is 4 root x du is all right, but okay, so we need this root x. So u squared is equal to root x plus 1. So root x is equal to u squared minus 1. So this is 4 u squared minus 1 du. And that's the entire integrand. So we've got, take out the 4. Well, let's bring this over here. Yeah, this is going to work. Pretty cool. There we go. So we've got this is okay. So, but u is this here. So let's just write this in the neatest form. plus c. That's it. Okay, here's one of those where we have a rational function, but we can't factor the denominator anymore. So we can't do partial fraction decomposition on this. Okay, so can we solve it? Well, we could just try substitutions. So here, there's no we can't say u is equal to x squared and then get like a x dx, right? Where we have an x dx. So we can't use the traditional substitution, but we can still play with substitutions, right? So if we said that u is equal to x to the fourth plus 1, I mean, we do have an x squared plus 1 squared, so we can consider a trig substitution as well. So we've got du is 4x cubed dx. Okay, so, well, okay, actually, let's do this. Let's say that, I'm not sure how well that would have worked, but if we say that u is equal to x squared, okay, so u is equal to x squared, therefore, so u squared is x to the fourth, and du is 2x dx, okay, so du over 2x is equal to dx. Because, right, that's all we have is just remaining is dx. Now, x is equal to root u, right? We can see that here. X is equal to root u. So let's just put that in. Okay. So we've got 1 over root u times 1 over u squared plus 1 times dx, which is 1 over 2 root u du. Okay. Root u times root u, let's take out the 1/2. Root u times root u is u and yeah, there okay, so we can solve this. So let's put this up here. So let's do partial fraction decomposition on this. Okay, so clear the fractions. So we've got a u squared plus 1 plus u. Okay. Wait. No. Okay, when u is equal to 0, a is equal to 1. Okay, when u is equal to 1, we've got 2a, and then p plus c is minus 1. Okay, when u is equal to minus 1, we've got so 2 minus c plus b is equal to 1. So b minus c is equal to minus 1. So b plus c is equal to minus 1. b minus c is equal to minus 1. So one of these is going to have to be 0. 2c is equal to 0. C is equal to 0. So b is equal to minus 1. So we've got a is equal to 1, and then b is minus 1. Okay. So what we've got is so we just decompose this. So we want to make sure, don't forget that this 1/2 factor, 1/2 minus okay, so we could just here do a substitution that z is equal to u squared plus 1. And what we'll get is, so we can do this mentally. So we've got this should just be, okay, now the derivative of the natural log of u squared plus 1 is 1 over u squared plus 1 times the derivative of u squared plus 1 is 2u. So we need to add a 1/2 factor. Okay. So u is equal to x squared. X squared is always positive. So we can remove the absolute value. X to the 4th is always positive. Okay, there we go. Okay, so I see the secant theta, tangent theta, d theta, and I think that's the derivative of secant theta. And then outside of that, I see only secant thetas, so absolutely we want to say that u is equal to secant theta. Therefore, du is secant theta, tangent theta, d theta. And so we've got u squared minus u du. Okay, so we can factor out a u down here. Okay, and then we just, so let's not, instead of doing the full partial fraction decomposition process, this is easy enough to where we can do this mentally. Okay, so if we had a 1 and a 1 here, and let's say we added them, you'd have u minus 1 over here, and then u over here. So u minus 1 minus u, you'd end up with minus 1. That's not right. So what if we did this? So you have u minus 1 over here, and then minus u over here. Okay, so we need a 2. We need a 2 over here. Let's put a minus. So we would have 2 times u minus 1 minus u. Okay, so let's just do the decomposition. So we've got u times u minus 1. 1 is equal to a times u minus 1 plus b times u. If u is equal to 0, we've got minus, so a is equal to minus 1. If u is equal to 1, you've got b is equal to 1. Didn't I try that? So oh, I didn't put it. Okay. I didn't put a minus in the first slot. And then plus. So that would be, you'd have minus u minus 1 plus u. Minus u plus u is 0. Yeah, okay. And then minus minus 1. Okay. So we've got the integral of so this is and so combining these two, you've got so plugging in secant theta for u, and we can actually write this as 1 minus 1 over secant theta is cosine theta plus c. Okay, just looking at this, to me, I think integration by parts. There's no need to separate sine 2t into 2 sine t, cosine t. To me, this is a classic integration by parts where you set u equal to t and dv equal to sine of 2t dt. Because then the t goes away, and then we don't get anything more complicated here. We just get, and then, well, we need the minus, because cosine 2t is minus sine 2t. Okay, and so u times v okay, evaluated from 0 to pi over 6 minus the integral of v du. So take out the minus 1/2. Okay, so 1/2, or no, minus 1/2 times pi over 6 times cosine of 2 pi over 6 pi over 3, okay, minus 1/2 times, oh, well, that's going to be 0 no matter what. Cosine of 0 is 1, but, okay, so that's it, okay, plus 1/2, and then this integral is 1/2 sine 2t, so 1/4, and then sine 2t evaluated from 0 to pi over 6. Okay, so minus pi over 12, cosine of pi over 3 is what? One-half. Okay. Sine of 0 is 0, so we just have sine of pi over 3. Minus pi over 24. Sine of pi over 3 is what? Root 3 over 2. So that's, okay, so this is, there we go. Okay, so rational function, we've got x times, or the order of the numerator is less than the order of the denominator, so we factor the denominator, Okay, now that the denominator is fully factored, let's do partial fraction decomposition. We've got two linear factors to the first power. So the form of the decomposition is this. Now let's clear the fractions. Okay, so we've got x minus 1, a. Okay, so when x is equal to 0, you've got minus 1 is equal to 2a. So a is equal to minus 1/2. When x is equal to minus 2, you've got minus 3 is equal to minus 2b. So b is equal to 3/2. Okay. So this integral is equal to okay, so and that's it. Okay, so I think cosine x dx, so u is equal to sine x, du is equal to cosine x dx, but we've got this x here, which makes things a little bit complicated. Now, I think about the half angle formula, so sine squared x is 1/2 times 1 plus cosine 2x, which is nice, but then you're multiplying cosine 2x and cosine x, and there are trig identities that deal with that, right? I think so. Yeah, like cosine x. Okay, so let's, well, then we have something like this, which is, we don't know how to integrate this. If we had cosine x times cosine 2x, and we could break it down into this, a form like that, but that's, I don't know how we're going to integrate this. We don't want to go here. Okay. Let's just see. I'm just curious if we said, because we might have to integrate inverse sine of x, and I think we could do that. If we said u is equal to sine of x, then du is cosine x dx, and we see that then x is equal to inverse sine of u. Okay, and so what we're left with is u squared inverse sine of u du, which is doesn't look much easier. So I don't know about that. Well, okay, if we come to our trig, the derivatives of trig, inverse trig functions, the derivative of inverse sine is 1 over the square root of 1 minus x squared. I mean, I definitely think we could solve it using integration by parts if we take the derivative of inverse sine u and then put u squared as the dv. What we'd end up with, we'd have to find an integral of like something like u cubed over the square root of 1 minus u squared, which we could do that like a trig substitution. We could do that. Okay, and to me, I can't see any other way to simplify this. That, I don't think I'm missing some quick way to do this. So to me, this is it. We need to just go ahead and do this. So, okay. We've got the integral of u squared inverse sine of u du. So integration by parts, we're going to say that z is equal to u, no, inverse sine of u, because we're going to take this derivative. And then dp is equal to u squared du. Therefore, dz is equal to 1 over the square root of 1 minus u squared. So, and then put the du here. Okay, p is equal to 1/3 u squared. All right. So z times p minus the integral of, and it's going to be p dz. So take out the 1/3, and we've got or wait, no, this should be u. Okay, wait. This should be u cubed. So this should be u cubed, and this should be u cubed. All right, now we can do a trig substitution here. And we're not going in circles. You might say, oh, we're going to do a trig substitution and come back here. No, because we've performed the integration by parts. This is a new integral, right? We've broken down the integral we're trying to solve. This integral, we've gotten a piece of it. So this is another piece. This is a new integral. Okay, so let's come off to the side and do so we want to do the trig substitution. We've got 1 minus the variable squared. So we want to use this. So x is equal to sine theta. The variable is equal to sine theta. We want to make the substitution that u is equal to sine theta. Therefore, du is cosine theta d theta. Okay, square root of 1 minus u squared equals to the square root of 1 minus sine squared theta, which is equal to the square root of cosine squared theta, which is equal to cosine theta. So cosine theta, and then sine cubed theta, and then cosine theta d theta. So we've got sine cubed theta d theta. How do we solve this? What we do here with an odd power of, if we have a sine or a cosine to an odd power, sine or a cosine to an odd power by itself, we separate it up into like a sine squared theta, sine theta d theta. Okay, then we do this. Sine squared theta is 1 minus cosine squared theta. Okay, now we're going to need another variable to substitute. We've got, so q is equal to cosine theta. So dq is minus sine theta d theta. Okay, so we've got, take out the minus for the dq, 1 minus q squared dq. So what is this? This is minus, then q minus 1/3 q cubed. 1/3 q cubed minus q. 1/3 cosine cubed theta minus cosine theta. Okay, but if we draw the triangle, okay, but now we need to get back to the original variable. So theta, we said that u is equal to sine theta. U divided by 1 is equal to sine theta. Sine theta is opposite over hypotenuse. Opposite over hypotenuse. Okay, now what is this side? This side squared plus this side squared is equal to 1 squared. So this is going to be 1 minus the square root of 1 minus u squared. Okay, so what is cosine theta then? Adjacent over hypotenuse. Okay, so what is this? 1/3 cosine theta cubed. So that's going to be and then minus just cosine theta. Okay, so let's clear all this. What we have is this is okay, so let's put this in here. We can distribute the minus 1/3. So minus 1/3. Well, I don't want to get confused. So, well, no, we can do that. All right, let's see. Minus 1/3 times positive 1/3. So 1/9. And then positive 1/3. There we go. Okay, but we're not done because we've solved this integral, right? But we need to, we said u is equal to sine x, right? The original integral is in terms of x. So we've got 1/3 sine cubed of x, inverse sine of sine of x, which is going to be just x. So we'll come back and simplify. 1/9, 1 minus sine squared x, which that's going to be cosine squared x. Okay. So we've got 1/3, and then the inverse sine of x is x. Okay. 1 minus sine squared x is cosine squared x. So cosine of x squared to the 3/2 power is just to the 3 times 3/2, so that's cosine cubed of x. Okay, plus 1/3, 1 minus sine squared x is cosine squared of x. Square root of cosine squared x is cosine x. And there we go. Okay, so looking at this, I feel like we could try u is equal to 2x, or the substitution u is equal to 2x, or maybe u is equal to 1 plus 2x. To me, if one of those would work, then I feel like the other one would work as well. But, whenever we rationalize, if we have a radical, we do everything under the radical. And so to me, this is a similar concept. This isn't a radical, but still. It's like a square. It's like something of this expression kind of trapped inside this squared. So let's say that I'm thinking, let's say that u is equal to 1 plus 2x. But again, I think let's say this works. I feel like if you tried u is equal to 2x, that might work as well. So then du is equal to 2 dx. So 1/2 du is equal to dx. Okay, so When x is equal to 0, u is equal to 1. When x is equal to 1/2, u is equal to 2. Okay. Now, x is equal to, so 2x is equal to u minus 1. So x is equal to u minus 1 divided by 2. 2x is equal to u minus 1. Okay, and then we've got u squared in the denominator. And then dx is equal to 1/2 du. Okay, so we've got, take out the 1/2. Well, actually, we've got two 1/2s. So take out both 1/2s. We've got 1/4 from 1 to 2. Well, actually, this is, okay. This is e to the u times e to the minus 1, right? So what we could do is we could take out a 1/4e. Right? So we've got u minus 1 e to the u over u squared du. And this is still kind of complicated, but it's definitely, we've improved from the initial integral. Okay. And one of the ways that we've improved is, since we substituted the entire denominator, like u is equal to this entire expression under the squared, we've got a single term in the denominator here. So that's nice with integrals, because we can separate that into separate integrals. Okay, so u e to the u divided by u squared is e to the u over u minus e to the u over u squared du. Okay, so we've got all right, 1 to 2. We need to solve these two integrals. In fact, let me write it like this. Okay, so now let's take each of these separately. If we've got one thing I'm noticing, that if we say that if we make the z equal to 1 over u, then dz is minus 1 over u squared. We're going to end up, this will simplify this entire expression, so you'll see what I mean. So dp is equal to e to the u du, so p is equal to e to the u. So we've got z times p, evaluated from 1 to 2, minus the integral of p dz, take out the minus, e to the u over u squared du. And actually, this goes from 1 to 2. And this doesn't just simplify it, but if you notice, so this is this here. So when we substitute this in here, what happens? These two subtract out. So what we've got is that this, all of this, is just equal to that. Okay? So we've got e squared divided by 2 minus e divided by 1. So 1 over 4e times e squared divided by 2 minus 1 over 4e times e. E over 8 minus 1/4, and that's it. Okay, looking at this, I think about rationalizing, so saying that u is equal to the cube root of x, but then I also think about the multiplying by the conjugate. However, this is a little bit different in the sense that, so like, you know, if we had square root of x times the square root of x, that eliminates the radical. But with other roots that aren't, you know, of 2, index 2, it doesn't work out that cleanly. Because x to the 1/3 times x to the 1/3 is x to the 2/3. Okay? So in that case, let's go ahead and try that u is equal to the cube root of x. All right? So in that case, we've got u minus 1 over u, or under u plus 1. Okay, and then for the dx, let's cube both sides. And now take the derivative of this entire equation with respect to x. 3u squared du dx is equal to 1. Therefore, 3u squared du is equal to dx. So, okay, let's bring this. So, 3u squared du dx is equal to 1. Therefore, 3u squared du is equal to dx. Okay, so we've got, let's bring this down here. U minus 1, u plus 1 times 3u squared du. So we've got u cubed plus u squared over... Okay, so we've got a rational function here, which we can solve. So the first step is we look and see, is the order of the numerator less than the order of the denominator? And it's not in this case, so we need to do, let's do polynomial long division. Okay, so, all right, u cubed divided by u is u squared. U squared times u minus 1, u cubed minus u squared. Subtract these two. U squared plus u squared is 2u squared plus 0u. 2u squared divided by u is 2u. 2u times u minus 1. 2u squared minus 2u. Subtract these two. You've got 0 plus 2u. Okay, 2u divided by u is 2. 2 times u minus 1 is 2u minus 2. Subtract these two. You're left with 2. Okay, so u cubed plus u squared divided by u minus 1 is equal to u squared plus 2u plus 2 plus 2 over u minus 1. Okay, so we've got 3 u squared plus 2u plus 2 okay. So we've got separating this into separate integrals. 6 plus okay. So we've got u cubed plus 3u squared plus 6u plus 6 natural log of the absolute value of u minus 1 plus c. Okay, but u is equal to the cube root of x. All right, cube root of x cubed is just x. Cube root of x squared is 3, or it's x to the 2/3. So we've got 3x to the 2/3. And then 6, I'll just do x to the 1/3 plus 6 natural log of the absolute value of x to the 1/3 minus 1 plus c. And that is the integral. Okay, I see this x squared minus 1 squared, especially under a square root, I think trig substitution. So let's do that. We've got x squared minus a squared, so we want to say that x is, with a is equal to 1, so we want to say that x is equal to secant theta. Therefore, dx is equal to secant theta tangent theta d theta. So x squared minus 1 is secant squared theta minus 1, the square root. Secant squared theta minus 1 should be tangent theta. It is. Or tangent squared theta. Okay. So we've got, all right, when x is equal to 1, theta is equal to inverse secant of 1, which is 0. When x is equal to 2, we do inverse secant of 2, pi over 3. Okay. Now, x is secant theta. Square root of x squared minus 1 is tangent theta. And then dx is secant theta tangent theta d theta. Okay, so tangent squared theta d theta. Okay, and I think about, when I see tangent squared theta, I think about the fact that we can turn that into a secant squared theta with tangent squared theta is secant squared theta minus 1, and secant squared theta is great for integration because its integral is equal to tangent theta. So right, so we can, this is tangent theta minus theta, and evaluated from 0 to pi over 2. And what's nice about the definite integral is that we don't have to back substitute to get back to x, because we can just evaluate it here because we updated the limits of integration. And what am I doing? This is pi over 3. Okay, so tangent of 0 is 0, 0 minus 0 is 0, so this is just equal to tangent of pi over 3 minus pi over 3. Tangent of pi over 3 is root 3. And that is the integral. Okay, so looking at this, I think about the conjugate, so multiplying by 1 in the form of 1 minus tangent theta over 1 minus tangent theta, because that should simplify the denominator. And then also, I'm not upset about having a tangent squared theta. However, what we're going to do is we're going to write this. We're going to break up the tangents into sines over cosines. Okay, and then now we're going to multiply this by 1 in the form of cosine over cosine. So what we get is okay, so that's the integral. We can let's write it like this. Okay, and so what you can see here then is if we say that u is equal to sine theta plus cosine theta, then what is du? Du is cosine theta minus sine theta d theta, which is in the numerator. So what we've got is the integral of 1 over u du, natural log of the absolute value of u plus c. So natural log of the absolute value of sine theta plus cosine theta plus c. Okay, so cosine of the square root of t, the square root makes this kind of complicated. And so to me, I think about, the idea of rationalizing. So if we say that u is equal to root t, this could potentially simplify this to something that we can solve. So u squared is equal to t. So 2u du dt is equal to 1. So 2u du is equal to dt. So we've got cosine of u times 2u du. Okay, and yeah, this is something that we can work with. We can solve this using integration by parts. And so we're going to leave out the 2 for the moment. We're going to say that we're going to say that z is equal to u, because both of these are easy to integrate and differentiate. So if we had a choice, we want to differentiate the u. All right, so then dp is equal to cosine u du. So therefore dz is equal to du, and p is equal to the sine of u. So u cosine u du is zp minus the integral of p dz. Which is u sine u minus integral of sine u is minus cosine u. Okay, so we've got so 2u sine u plus 2 cosine u. All right, but u is equal to root t. Okay, plus c. That is the integral. Okay, so we've got a single term in the denominator, so I want to think about separating this up into two separate integrals. So we've got x e to the x over x squared, so e to the x over x dx. Okay, and then e to the x all right, so I think we had a similar problem to this earlier, but let's do integration by parts here. And what we're going to do is we're going to say that u is equal to 1 over x, and dv is equal to e to the x dx. Because we're going to get, with du, we're going to get minus 1 over x squared dx, and that has a similar form to this, and so it could end up simplifying really well. That's what happened earlier. All right, so uv minus the integral of v du, take out the minus, yeah, so exactly. What's going to happen is, so this is equal to e to the x over x plus and then minus so this subtracts out and we're just left with, and that's the integral. Okay, looking at this, I think about the idea of rationalizing, but we don't have a fraction here, but still, it'd be nice to get rid of the radicals and replace the radicals with just power terms. So we say that u is equal to the entire radical expression, and now we're not going to take the derivative here because we don't have a 1 over 2 or a 1 over root x dx type term, so we're going to say u squared is equal to x, and now take the derivative of this entire equation with respect to x. So we've got 2u du dx is equal to 1. So 2u du is equal to dx. So you got u e to the u times 2u du. Yeah, this should work well. So then we've got u squared e to the u du. And we can use integration by parts on this. And we might have to do integration by parts twice. But that's fine. Okay, so we're going to say that z is equal to u squared, because u squared is, both of these are easy to differentiate and integrate, but if we had a choice, we want to differentiate u squared, we want to reduce it. dp is equal to e to the u du. dz is equal to 2u du. P is equal to e to the u. So u squared e to the u du is z times p minus the integral of p dz. Okay, so now we're going to plug this in here, and we get, let's multiply by 2. So 2u squared e to the u minus 4. Okay. So now let's do integration by parts again. Z is equal to u. dp is e to the u du. dz is du. P is e to the u. Z times p minus the integral of p dz. Okay, so now we want to multiply the minus 4 here. So minus 4u e to the u plus 4e to the u. Okay, so we can factor out a 2e to the u, and we've got u squared minus 2u plus 2. All right, plus c. But u is equal to root x. So 2e to the root x. Root x squared is x minus 2 root x. And there we go. Okay, looking at this, I see 1 squared plus x squared, and especially since it's under a square root, I think trig substitution. Okay, so we've got this form here, a squared plus x squared, so we want to say that with a is equal to 1. So we want to say that x is equal to tangent theta. So x is tangent theta, therefore dx is secant squared theta d theta. Okay, if we substitute this into the square root of 1 plus x squared, we get 1 plus tangent squared theta squared root of 1 plus tangent squared theta. 1 plus tangent squared theta is secant squared theta. So secant theta. Okay. So when x is equal to 1, then theta is equal to inverse tangent of 1, which is pi over 4. When theta is equal to root 3, or no, when x is equal to root 3, theta is equal to inverse tangent of root 3, which is pi over 3. Okay, x squared is tangent squared theta. Square root of 1 plus x squared is secant theta. And then dx is secant squared theta d theta. Okay, so now we need to solve this trigonometric integral here. And so, yeah, we've got a secant squared theta, d theta, and so the derivative of tangent theta is secant squared theta, but we would have a secant theta left over. And so this is one of those where we have to sort of play with this to figure out, to put it into a form that we can integrate. And so what we're going to do is we're going to let's turn this into sines and cosines. So let's first go ahead and so secant cubed theta okay, so secant cubed is 1 over cosine cubed. And then tangent squared is, in the denominator, is cosine squared over sine squared. So this is sine squared theta cosine theta, all under 1, okay? Now, we still don't have a, we couldn't say u is equal to sine theta, because then, yeah, du is cosine theta d theta, but this cosine theta is in the denominator. And the idea is we want to potentially get like a cosine theta d theta, and then with everything else being sine. And we can do that if we multiply this by 1 in the form of cosine theta over cosine theta. And so what we get is right, but cosine squared theta, we know, is 1 minus sine squared theta. And this we can work with. So okay, so we can work with this because we can now say that u, make a substitution, u is equal to sine of theta. Therefore, du is cosine theta d theta. And so when theta is equal to pi over 4, u is equal to root 2 over 2. When theta is equal to pi over 3, u is equal to root 3 over 2. And what's nice about with the definite integral is that we're not going to have to, all these substitutions we're making, we're just carrying, we're updating the limits of integration, so we don't have to ever go back. Okay, so what we've got is u squared and there we go, and we can solve this, right? Okay, so we want to use partial fraction decomposition to separate, to break this rational function down. And so we see that the order of the denominator is less than the order of the numerator, so we can go ahead and now go to the step of factoring this. And so we've got u squared, 1 plus u, 1 minus u. Okay, and that's fully factored. So now let's write the form of the decomposition. So we've got, we'll do it like this, u plus 1, and then we'll say minus u minus 1, like with the b. You see, we can make this a little bit, look a little more symmetrical, right? We've changed the 1 minus u to u minus 1. Okay, and then plus u squared cx plus d. Okay. So now we want to clear the fractions, multiply by the least common denominator. So we've got 1 is equal to a minus b plus cx plus d Okay, so if u is equal to 0, then we've got, oh, why do I always do this? This is a u, not an x. Okay, so if u is equal to 0, then we've got 1 is equal to d times 1 times minus 1. So d is equal to minus 1. If u is equal to 1, then we've got, this goes to 0, this goes to 0, so we've got minus b times 1 times 2. So b is equal to minus 1 over 2. If u is equal to minus 1, then these two go away and we're left with minus 1 is minus 2. So a is equal to minus 1/2. All right, now if u is equal to 2, we've got, so let's make some room here. Right, 2 minus 1 is 1. 2 squared is 4. 4 times minus 1/2 is minus 2. Okay, now b is minus 1/2, so plus 1/2 times 4 times 3 plus 2c minus 1. Okay, 2 plus 1 is 3. 2 minus 1 is 1. Okay, so we've got 1 is equal to minus 2 plus 6 plus 6c minus 3. Okay, 1 is equal to minus 2 plus 6 is 4, and then 4 minus 3 is 1, so C is going to be equal to 0. All right, so we've got A is minus 1/2. B is 1/2. Or B is minus 1/2, so we'll bring the minus. And then the cx plus d is just going to be this. Like that. Okay, so we've got so okay, now let's go ahead and get this integral here and simplify it, and then we'll apply the limits. So we've got minus 1/2 natural log of the absolute value of u plus 1 plus 1/2 natural log of the absolute value of u minus 1 plus 1 over u. Okay, and so this is 1/2 natural log of the absolute value of u minus 1 over u plus 1 plus 1 over u. So now let's evaluate this from those limits. So we've got 1/2 natural log of the absolute value of plus 2 over root 3 minus 1/2 natural log of the absolute value of root 2 over 2 minus 1 root 2 over 2 plus 1 plus 2 over root 2. Okay, so we've got root 3 divided by 2 minus 1 divided by root 3 over 2 plus 1. 4 root 3 minus 7. Oh, and then is 4 root 3 minus 7 positive or negative? Negative. So 7, we want to write that as 7 minus 4 root 3 so we can remove the absolute value. Okay. So next we've got, let's see, we can use this. So root 2 over 2 minus 1, and then root 2 over 2 plus 1. 2 root 2 right, minus 3, is that positive or negative? That is negative, so we want to make it 3 minus 2 root 2. And then minus 2 over root 2. Okay, 2 over root 2 should just be, if we multiply this by root 2 over root 2, this is 2 root 2 over 2, so this is just root 2. Okay, so we've got 1/2 natural log of what is 7 minus 4 root 3 divided by 3 minus 2 root 2. And actually I can just divide those two because, yeah. So 7, if I just divide these two, I'll get the same answer. Okay, and it doesn't really simplify, so I'll just leave it 7 minus 4 root 3 divided by 3 minus 2 root 2 plus 2 over root 3 minus root 2. And that is the integral. Okay, and checking the answer, this is the correct magnitude, but I missed a minus sign somewhere. So it should be multiply this times minus 1. Multiply this times minus 1. So I think you get the idea of how to solve the integral. I forgot a minus sign. I messed up a minus sign somewhere. So it would be make this plus, make this minus, and then you could put a minus here, or you could just flip these. Put the 7 minus 4 root 3 in the denominator and 3 minus 2 root 2 in the numerator. Okay, so I'm looking at this, and I think trig substitution, we could say that u is equal to 2x. Therefore, u squared is equal to 4x squared. And so we've got u squared minus 1 under the square root. So variable squared minus constant squared, that's this form. So the a squared is, or a is 1. So we want to say that x is equal to, or the variable is equal to secant theta. So the variable is equal to secant theta, but u is equal to 2x. So we want to say that x is equal to 1/2 secant theta. That's the substitution we want to make. So x is 1/2 secant theta, therefore dx is 1/2 secant theta tangent theta d theta. And so now making the substitution, so 4 times x squared is 4 times 1/4 secant squared theta, which is just secant squared theta, minus 1. Secant squared theta minus 1 is tangent squared theta. Okay, so x squared is 1/4 secant squared theta. Square root of 4x squared minus 1 is tangent theta. Dx is 1/2 secant theta tangent theta d theta. Okay, so 1/2 divided by 1/4 is 2. Okay, and we've got 1 over secant theta is cosine theta. So 2 sine theta. All right, but we need to get back in terms of x. And so let's draw the right triangle. Okay, so what we have is secant theta is equal to what? 2x divided by 1. So secant is 1 over cosine, so cosine theta is equal to 1 divided by 2x. Cosine is equal to adjacent over hypotenuse. Okay, so 1 squared plus this side squared is equal to 4x squared. So this is the square root of 4x squared minus 1. Okay, So sine theta, which is what we need, is opposite over hypotenuse. Okay, so 2 sine theta is there you go. All right, so looking at this, I'm wondering what is the derivative of arc sine? So, okay, 1 over the square root of 1 minus x squared, which is kind of in here. Okay, what we can do is let's separate this into 2 separate integrals. Okay, we can solve these separately because here we can make just a substitution because we have a x dx on the outside. So, okay, here we're going to say that u is equal to 1 minus x squared. Therefore, du is minus 2x dx. So, right? So we've got square root of u, and then x dx is minus 1/2 du. Okay, so this is which is, so u to the minus 1/2 plus 1/2 is 1/2. Divided by 1/2. This is going to be minus root u. Okay. Now we're going to do a u substitution here. We're going to say that u is equal to inverse sine of x. Therefore, du is, we just looked at this, 1 over the square root of 1 minus x squared dx. Okay, and so what we've got is just u du. Well, okay, let's substitute back. Yeah, okay, we didn't finish this. U is what? 1 minus x squared. Okay, here 1/2 u squared. But what is u? U is inverse sine of x. So this integral is equal to 1/2 inverse sine of x squared minus square root of 1 minus x squared plus c. Okay. So I see a natural log of t, and I know that the derivative of natural log of t is 1 over t. So we should be able to do this integral with saying that u is equal to natural log of t. Therefore, du is 1 over t dt. And so we've got sine of u du. Okay, we're getting into some easy integrals here. This is minus cosine of u plus c minus cosine of the natural log of t plus c. Okay, so just looking at this, it's tempting to go ahead and expand this out. And it might seem like that's going to make it more messy, but but to me, it allows you to separate it into create separate integrals, which always seems like that's when if you've got no other way to go, then go that way. So, okay, the derivative of tangent x is secant squared. We don't have a secant squared. So, yeah, let's go ahead and do, so 1 plus 2 tangent x plus tangent squared x secant x dx. So we've got secant x plus 2 tangent x secant x plus tangent squared x secant x dx. All right, so secant x dx, we can solve that. 2 tangent x secant x dx. So I feel like we should be able to solve these. So, all right, well, secant x we can get from the table of integrals. Integral of secant x is natural log of the absolute value of secant x plus tangent x. Okay. Here, we don't have a secant squared x that we can separate out, or a, well, okay, secant x tangent x is the derivative of secant x. So maybe we could do that, but let's see. Okay, sine x over cosine x times, and then secant is 1 over cosine. So sine x over cosine squared of x. Yeah, we can do that. So two. And why is this going to work? Because we have the sine x dx in the sine of x is in the numerator. If it was flipped, it wouldn't work. Well, no, it would work. Yeah, we had issues previously with when we had both the sine x and the sine and the cosine in the denominator, so we couldn't do anything with that. Like if we had cosine squared x sine x, we couldn't do this simple substitution. But here we can say u is equal to cosine x. So minus du is sine of x dx. So this turns into, bring out the minus, and we've got, okay, the integral of 1 over u squared is minus 1 over u, so we've got 2 over u, so 2 over cosine x. Okay, now we should be able to do a similar thing here. So sine squared x over cosine squared x, 1 over cosine x. Okay, no, this might not work out as well because we have the sine squared x. And you could say, well, that's equal to 1 minus cosine squared x, but if this was sine cubed x, we'd be okay. Because we could take out a sine of x, and then we're left with a sine squared x, and we can turn that into a cosine and then make the substitution. But, well, okay. No. We're actually, what am I talking about? All we need to do is, we have a tangent squared, or wait, no, that's, I thought we had a secant. If we had a secant squared, it would be good. Well, no, okay, what we do is, we turn this into, so tangent squared is secant squared minus 1. Okay, so let's, this integral here, we'll come off to the side and do this. So this is secant cubed x, which they solved this in the textbook, minus secant, the integral of secant x dx, and that will subtract out here. So actually what we can do is, what we've got is, we can erase this, and what we're left with is right? Now we can go to the textbook to get the integral of secant cubed x dx. They solved this. Yeah, here it is. So, well, we actually, why not do this? We could say 2 secant x, 1 over cosine of secant, okay, plus 1/2 secant x tangent x plus 1/2 natural log of the absolute value of secant x plus tangent x plus c. And there we go. That is the integral. Okay, I see that sine of 2x, and I think about the identity 2 sine x cosine x. And so with this here, let's go ahead and do that. You know, normally we'd rather, with integration, we'd rather the sine of 2x than to split it up. But in this case, it's a little bit different. So okay, so we've got so take out the 2, and you've got cosine to the 4th of x sine x dx. And yeah, we can solve this, no problem. So u is equal to cosine x. Du is minus sine x dx. So minus du is sine x dx. And so this integral is, okay, when x is equal to 0, u is equal to 1. And then when x is equal to pi over 2, we know that cosine of pi over 2 is 0. Okay, so then we've got u to the 4th du. Okay, so bring out the minus sign. All right, so this is minus 2, and then 1/5 u to the 5th evaluated from 1 to 0. So minus 2/5, then u to the 5th evaluated from 1 to 0. So 0 minus 1. So 2/5. Okay, x hyperbolic cosine h of x dx. To me, let's just do integration by parts. U is equal to x. dv is equal to hyperbolic cosine of x dx. So du is dx. V, we know that hyperbolic, the derivative of hyperbolic sine of x is hyperbolic cosine of x, just like regular trig functions. Okay, so x hyperbolic cosine of x dx is, so u times v minus the integral of v du. Okay, so now the integral of hyperbolic sine, this is different in the sense that the derivative of the hyperbolic cosine of x is just equal to positive hyperbolic sine of x. So this is just like that, plus c. Okay, so I see a 1 over x dx in a natural log of x. And actually, well, okay, let's do, if we said that u is equal to natural log of x squared, okay, then du is equal to what? It's going to be 2 natural log of x times the derivative of natural log of x is 1 over x dx. And so we've got 1/2 du is equal to natural log of x over x dx. And we've got that. So yeah, that's going to be the substitution. So we've got the square root of 1 plus u there we go. Okay, but now how do we solve this? Well, what we do is we write this as, so let's say u plus 1 to the minus 1/2. Okay, and then we can use the power rule of integration. And we would usually say like z is equal to u plus 1, make a substitution, but this is so simple since the derivative of u plus 1 is just 1. So we can, all we have to do is just act like this is a single variable. So the power rule of integration, we say u plus 1 to the minus 1/2 plus 1/2 is 1/2 over minus 1/2 plus 1/2. Okay, so we get u, the square root of u plus 1. Okay, but what is u? U is the natural log of x squared. There we go. Okay, so we've got a rational function, a ratio of two polynomials. One is a polynomial, and then this is a polynomial. So we can do the partial fraction decomposition. So, okay, we first check to see is the order of the numerator less than the order of the denominator. It is. So next, we want to factor the denominator. Okay, so we've got, so 2 times 1, so we can write this as 2t squared plus 2t plus t plus 1, right? Factor out a 2t over here. Now we can factor out a t plus 1. Okay, so we've got, all right, so that's fully factored. We've got 2 linear factors to the first power, so let's write the form of the decomposition. Okay, now let's clear the fractions, multiply by the least common denominator. So we've got, okay, so if t is equal to minus 1, then we have, so a is equal to minus 1. If t is equal to minus 1/2, we have minus 1/2 plus 1 is 1/2. So b is equal to 2. So we've got, okay, so what we have is this integral is Okay, and so what we want to do is separate this into two separate integrals. Okay, now when we have linear factors, well, let's do this. Okay, when we have linear factors, no matter, even if they're raised to a power, a u substitution for the linear factor will always work. But here they're raised to the power 1, so we could probably just do this mentally. So the integral of 1 over 2t plus 1 is going to be natural log of the absolute value of 2t plus 1. And then if you differentiated that, you'd get a times 2, so you want to, it'd be 1/2. And so 1/2 times the natural log of the absolute value of 2t plus 1. But we already have a 2 out here, so this is just going to be natural log of the absolute value of 2t plus 1, right? If you take this derivative, what do you get? You get 2 over 2t plus 1. Okay? And then this is the integral of, or the natural log of the absolute value of t plus 1. Okay, but we can simplify this because we can combine these. And there we go. That is the integral. Okay, so looks like just a rational function. And maybe if we, let's see what happens when we factor the denominator. Does that cancel with the x plus 2? So 4, 1. No, it doesn't, but this is just a rational function. Well, okay, well, what if we say that u is equal to x squared plus 3x minus 4, because then we're going to get just a first order polynomial when we take the derivative, which this is first order. 2x plus 3 dx. Could we put that in a similar form as this? I don't think so. No. So, okay, let's just do partial fraction decomposition. So, okay. Well, when we're integrating a rational function, we check and see is the order of the numerator less than the order of the denominator. It is. So we don't need to do polynomial long division. Next step is to fully factor the denominator. Okay. Now, so we've got two linear factors to the first power. So now let's write the form of the decomposition. This one would be pretty simple. Okay, now let's solve for a and b. Multiply by the least common denominator. So we've got x plus 2 is equal to okay, so when x is equal to 1, we've got 3 is equal to 5b. So b is equal to 3/5. When x is equal to minus 4, we've got minus 2 is equal to minus 5a. So a is equal to 2/5. Okay, so what we've got is the integral is equal to, so we can separate this up into, so take out this 2/5, and then we've got, okay, and then take out this 3/5, and we've got, all right, so 2/5 times natural log of the absolute value of x plus 4 evaluated from 2 to 4 plus 3/5 natural log of the absolute value of x minus 1 evaluated from 2 to 4. Okay, so 2/5 times natural log of 8 minus natural log of 6 plus 3/5 times natural log of 3 minus natural log of 1, which is 0. Okay, so we could say, we could turn this into natural log of 8 divided by 6, which is natural log of 4/3. So 2/5, well, let's do it this way. So 2 cubed is equal to 8. So we have 3 natural log of 2, right? This is 3 natural log of 2. So now we could say 6/5 natural log of 2 minus 2/5 natural log of 6 plus 3/5 natural log of 3. And we could actually take out a 1/5. Maybe this would look cleaner. So 6 natural log of 2 minus 2 natural log of 6 plus 3 natural log of 3. And actually the book simplifies it a little more than this. The book says so that we've got 2 to the 6th is 64. So natural log of 64 minus, then 6 squared is 36. And then 3 cubed is 27. Or the book doesn't do this. I typed it in my calculator to check the answer, and this is what it gave. So 64 divided by 36 is 16/9. Okay, then 27 times 16/9 is 16 times 3 is 48. So yeah, that's definitely simpler. Okay, so here, if we make a substitution that u is equal to 2x plus 1, we have x dx on the outside, so it doesn't work like perfectly like a ideal substitution. But to me, even if we do this, if we still do this substitution, there's a good chance that we end up with something we can work with, because we're going to get rid of this x expression cubed in the denominator. So, all right, so u is equal to 2x plus 1. So du is equal to 2 dx. So 1/2 du is equal to dx. When x is equal to 0, u is equal to 1. When x is equal to 1, u is equal to 3. Okay, so we've got u cubed, and then dx is, so 1/2 du. And then what is x? X is u minus 1 divided by 2. Okay, so we can take out that 1/2. And we've got right, there we go. And so why can we work with this? Well, one, because it's a rational function, but then even more than that, we've made this, we've flipped it to where we've got like the sum or subtraction of terms in the numerator and a single term in the denominator, and in which case we can split that up into separate integrals. So we got 1 over u squared minus 1 over u cubed. Okay, so we've got minus 1 over u, and then u to the minus 3, that's, okay, so that's u to the minus 2 over minus 2. So okay, evaluated from 1 to 3. And we can actually write, just to make this a little bit easier to visualize, we could say so we don't, it's less prone to make mistakes that way. So all right, plugging in 3, we've got 3 squared is 9. 9 times 2 is 18. Okay, minus 1 over 2 minus 1. Okay, so 1/18, and then 6 times 3 is 18, minus, okay, 1/2 minus 1 is minus 1/2, so minus 5/18 plus 1/2. 9 times 2 is 18. Minus 5 plus 9 is 4. And so we've got 1/18. Okay, so let's play with this denominator here. So sine squared x is 1 minus cosine squared x. Okay. So we've got 1 minus cosine squared x. Then we'll go ahead and leave this. All right. So we've got 1 minus cosine squared x minus cosine squared x. And then plus cosine to the 4th of x. Plus cosine to the 4th of x. So we've got 1 minus 2 cosine squared of x plus 2 cosine to the 4th of x. All right, now let's write this like in decreasing order of the power. So 2 cosine to the 4th of x minus 2 cosine squared of x plus 1. Okay, now when you look at sine x cosine x, what you can think about is that's like the derivative of sine squared of x or cosine squared of x, right? Because of the chain rule. So the derivative of cosine squared of x is 2 cosine x times the derivative of cosine x, which is minus sine of x. And so since we've got this in the denominator, we can see, right? So let's write this. We've got, this is equal to okay, what we can do is, let's say that, so we'll erase all this. Let's say that u is equal to cosine squared of x. Therefore, du is 2 cosine x times the derivative of cosine x is minus sine of x. So minus 2 sine of x cosine x dx So minus 1/2 du is sine x cosine x dx. There we go. So what we've got is, bring out the minus 1/2. We've got 2. Now, cosine of the u squared is cosine of the 4th of x. Okay, minus 2u. Okay, sine x cosine x dx is minus 1/2 du. There we go. And we can solve this. We have a quadratic factor, just a 1 over a quadratic factor. We know we can solve this. This is like fully decomposed. Well, unless we can factor this quadratic further. So can we factor this quadratic further? We check the discriminant, which is b squared minus 4ac. The discriminant is negative, so we can't factor this any further. So this is fully decomposed. It's fully decomposed, and with a quadratic factor to the first power and a constant in the numerator. We've talked about how to work with this in multiple videos. So, and unfortunately, this is looks like one of the more difficult cases. We've got the quadratic factor has a non-zero a, b, and c, and we have a leading term is non-1. So no problem, but it's just going to be kind of a pain. So what do we do in this situation? What do we do? Well, what we need is we need the quadratic in that x squared or variable squared plus constant or constant squared form. That's what we need. So we're going to need to complete the square. Okay, but we also need that x squared plus a squared form with the leading coefficient of 1. In this case, we'll need that. And so we need to start off by getting this quadratic to have the leading coefficient of 1. So what we're going to have to do is say that, so we're going to have to make multiple substitutions. So we start by saying that u is equal to, and this is going to be not so clean. We don't have if this was like 4u squared, that'd be nice. But so we're going to need to say that z is equal to root 2u. And we say this because now what is z squared? It's 2u squared. Okay, let me put this up here to save room. So z is equal to root 2u. Therefore, dz is equal to root 2 du. So 1 over root 2 dz is equal to du. Okay, so what we have is we can take out the 1 over root 2. Okay, so we've got z squared, and then, okay, what is 2 times u? U is 1 over root 2 times z, so 2 over root 2 is 2u is 2 over root 2, but I think 2 over root 2 is, so 2 root 2 over 2 is just root 2. So this is minus root 2z plus 1. Okay, and then du is 1 over root 2z. We already took out the root 2, so okay. So now we need to complete the square. All right, so when we've got a just variable plus constant squared is equal to x squared plus 2ax plus a squared. So in this scenario, 2a is minus root 2. So a is minus root 2 over 2. So what we've got is z squared minus root 2z plus a squared is 2 over 4 plus 1 minus 1/2. So this is z minus root 2 over 2 squared plus 1 minus 1/2. Okay. So what we've got is z minus root 2 over 2 squared plus 1/2. Okay. But now we need to say that m is equal to z minus root 2 over 2. Therefore, dm is equal to dz. And so what we've got is okay, now we've got this in the form that we need. Okay, we've got the integral of 1 over variable squared plus a constant with the leading coefficient just of the variable 1, d variable. So, okay, we come to this formula. And in this formula, a is equal to 1 over the square root of 2. 1 over root 2. So, okay, let's focus on this integral. Let's not worry about the leading coefficient. So, well, we can actually. Let's okay. So we've got. Let's do the whole thing. Okay. 1 over root 2 is just root 2. Okay. And then, so we've got root 2. So 1 over a is root 2. So root 2 times the variable. Okay. Now here. So we've got. Okay, so there we go. That's the integral, but we need to get back to x. So let's go down this long path here of substitutions. So m is equal to z minus root 2 over 2. So root 2z minus root 2 times root 2 over 2 is 1. Okay, but z is equal to root 2u. Root 2 times root 2u is 2u. Okay, but u is cosine squared x. And there we go. That is the integral. Okay, so, you know, I see a ratio of polynomials. So it's a rational function. And then, you know, the degree of the numerator is greater than the degree of the denominator. So let's do polynomial long division. X squared divided by x is x. X times x plus 2. Zero minus 2x. 2x, or minus 2x divided by x is minus 2. Minus 2 times x plus 2. 2 plus 4 is 6. So this is equal to x minus 2 plus, and we can absolutely solve that, no problem. So let's do it. Okay, so that's going to be 1/2 x squared minus 2x plus 6 natural log of the absolute value of x plus 2 plus c. Okay, here's a problem where, to me, the idea of rationalizing. So if we substitute u is equal to the entire radical expression, then we can end up with just like powers, which is easier to work with. So let's say u is equal to the cube root of x plus 3. Therefore, u cubed is equal to x plus 3 if we take the derivative, x plus c. Therefore, if we take the derivative of this entire equation with respect to x, we get so okay. Now what we have is, so x is equal to u cubed minus c. Cube root of x plus c is just u. And then dx is 3u squared du. So we've got u cubed. Yeah, exactly. This is going to be easier to work with. I mean, this is, we could solve this right now. So 3 times 1/7 u to the 7th minus c over 4 u to the 4th. Okay, but u is equal to the cube root of x plus c, so what we have is x plus c to the 7/3 x plus c to the 4/3. And there we go. And I forgot to this minus, there's this minus sign here. Right, we had a minus sign there. So, oh, and I might, it's not a good idea to put, we already have a c, so let me put another constant. Let's put k. Okay, so this is one of those where we've got a radical, and it would always be nice to get rid of that radical and replace it with powers. So let's just do u is equal to that entire radical. So u cubed is equal to x. Take the derivative of this entire equation with respect to x. So 3u squared du dx So 3u squared du is equal to dx. Okay, so we've got e to the u times, and then dx is 3u squared du. Okay, now this looks something like that we can work with. This u squared e to the u. I think if we do integration by parts twice, that'll work. So just focusing on the u squared e to the u, if we say that z is equal to u squared, and then dp is e to the u du, then dz is equal to 2u du, and p is equal to e to the u. Okay, so u squared e to the u du is z times p, u squared e to the u, minus the integral, could take out the 2 of p dz, so u e to the u du. Okay, so what do we have? We're going to multiply all that times 3. We've got 3u squared e to the u minus 6 u e to the u du. So we've reduced it down a little bit. Okay, so now let's do integration by parts again. Z is equal to u. dz is equal to du. dp is e to the u du. P is e to the u. Okay, so zp minus the integral of p du. Okay, so we've got multiplying that times minus 6. There we go. So there is the integral. We could take out a 3e to the u, and we've got u squared minus 2u minus 2. Okay, but u is equal to the cube root of x, so we have 3e to the cube root of x, and then x to the 2/3 minus 2x to the 1/3. I mean, we could do it like this. So the cube root of x squared minus 2. And there we go. Oh, plus c. All right, so here, if we write the secants as 1 over cosine, okay, and then we multiply by 1 in the form of cosine x over cosine x, then we get okay. Now we know that sine 2x is equal to 2 sine x cosine x. So we want to convert this sine x cosine x to sine of 2x. How do we do that? Well, we put a 2 here and then put a 1/2 in front. So now we haven't changed the equation, right? So what we have is okay, now we want to multiply this by 1 in the form of 2 over 2. So we've got okay, we bring that 2 out front. There we go. So now we've converted this to an integral that we can solve, because we can say that u is equal to sine 2x, therefore du is equal to 2 cosine 2x dx, and so 1/2 du is equal to cosine 2x dx, which we have here. So making this substitution, we bring out the 1/2, so the 2 goes away, and we've got u plus 2 du. Okay, and this is natural log of the absolute value of u plus 2, which is natural log of the absolute value of sine of 2x plus 2. So we can leave it like this. We could also simplify it by, so we write sine of 2x as 2 sine x cosine x. Okay, so then now we factor out a two. Okay, and now so natural log of a times b is equal to natural log of a times natural log of b, right? Well, plus, let me put the plus c. And so we've got, if we do that property, natural log of and then plus natural log of 2 plus c, right? But natural log of 2 plus c is just a constant. So you could write it like this too. Okay, so if we said u is equal to e to the x, let's do this. Because, yeah, if we said u is equal to e to the x, then du is e to the x dx, okay? And we do kind of have an e to the x dx, because we could say, right? E to the x times e to the x is e to the 2x. So what we have is 1 plus u. Yeah, there we go. Okay, so we've got a rational function here. The order of the numerator is the same as the order of the denominator, so we can just do polynomial long division to get the to separate this up. So u plus 0, and then u divided by u is 1. Then 1 times u plus 1 is u plus 1. Subtract these two, and you get minus 1. So this is 1 minus okay, so now we can integrate this. This is u minus natural log of the absolute value of u plus 1. But u is equal to e to the x. Okay, but e to the x is positive for all x values, and then adding 1 to that, it's positive, so we can just remove the absolute value. And there we go. Okay, so, I see this x squared, this power, like power term, multiplied by, a sine, a hyperbolic sine. This looks like an integration by parts problem. So let's say that, this is easy to integrate. So let's say that u is equal to x squared and dv is hyperbolic sine mx dx. Okay, so the integral of hyperbolic sine is going to be just positive hyperbolic cosine. Well, and then, we have the 1 over m as well. So 1 over m, because what we'll get, this derivative is hyperbolic sine positive mx times m. So that's what the 1 over m is for. And then du is 2x dx. Okay, so u times v minus the integral of v du. So let's take out the 2. Let's take out the 2 over m. Okay, so we've reduced it. Now we need to do integration by parts again. So u is equal to x. dv is equal to so du is equal to dx, and v is going to be the derivative of sine, hyperbolic sine is positive hyperbolic cosine. So it's going to be this, just the 1 over m hyperbolic sine mx dx. That's so with regular trig functions, the derivative of sine is cosine, the derivative of cosine is minus sine. With hyperbolic functions, the derivative of hyperbolic sine is positive hyperbolic cosine. The derivative of hyperbolic cosine is positive hyperbolic sine. Okay, so u times v minus v, the integral of v du. Bring out the 1 over m. Okay, so this integral is 1 over m hyperbolic cosine mx. So 1 over m squared hyperbolic cosine. All right, so we've got okay, so we've got okay, so we can combine the hyperbolic cosines. Well, actually, no. Let's just do this. So 1 over m x squared, okay, plus 2 over m cubed, okay, minus 2 over m squared x plus c. There we go. Okay, this looks just like a standard rational integral of a rational function. We first check to see if the order of the numerator is less than the order of the denominator. It is. Okay, so then we then want to fully factor the denominator. Let's take out an x squared. Okay, that's fully factored. We've got a quadratic factor. So quadratic factor is ax squared plus bx plus c. Here, b is equal to 0, c is equal to 0, a is equal to 1. Okay, we have a quadratic factor to the first power and a linear factor to the first power. So now let's write out the form of the decomposition. There's the linear factor. And then the quadratic factor. Okay, now let's solve for a, b, and c. We want to clear the fractions. Multiply by the least common denominator. So okay, so if we set x equal to 0, we get okay, if we set x equal to minus 3, we get all right, now if we set x equal to 1, we get, so 1 times a, okay, so b minus 1, all right, so minus 2 plus 4b minus 4 is equal to 1 plus 8 is 9. 9 minus 3 is 6. So 4b is equal to minus 2 minus 4 is minus 6. 6 plus 6 is 12. So b is equal to 12 divided by 4 is 3. So we've got, so a is minus 2. B is 3, and C is 1. Okay. So we've got okay, and now we want to separate this into two separate integrals. So 3x over x squared is okay, and then there we go. So we've got minus 2 natural log of the absolute value of x plus 3 natural log of the absolute value of x. Integral of minus 1 over x squared is minus 1 over x. And that's it. Okay, so let's just start, but let's see what happens when if we take the expression inside the radical and we multiply by 1 in the form of the conjugate over the conjugate of the denominator, we get, so okay, 1 plus x minus x, so this is 1 minus x squared. And then we've got up here x plus 1 squared. Okay, now if we take this square root, we've got Okay, now we can perform, okay, now here we could use a trig substitution. So what we've got is okay, so let's use a trig substitution. Okay, so we've got 1a squared minus x squared. That's the form with, so a is equal to 1. So we want to say that x is equal to sine theta. Okay, so x is equal to sine theta. Therefore, dx is equal to cosine theta d theta. All right, so the square root of 1 minus x squared is 1 minus the square root of 1 minus sine squared theta, which is the square root of cosine squared theta. Okay, so we've got cosine theta in the denominator, and then sine theta plus 1, and then dx is cosine theta d theta. Okay, so this is all right, and we've got so minus cosine theta plus theta. Okay, so now we need to go back to the x domain. So let's draw the right triangle. All right, we got sine theta is equal to x. So sine theta is opposite over hypotenuse. So this side squared plus this side squared is equal to 1 squared. So this is going to be the square root of 1 minus x squared. Okay, so cosine theta is equal to adjacent over hypotenuse. Okay, and then theta is going to be equal to inverse sine of x. So we've got minus plus c. There we go. Okay, so I feel like I want to multiply by 1 in the form of e to the x over e to the x, because two things will happen. We'll get an e to the x dx, and then this will go away. So that's what I'm thinking. So if we do that, we get e to the x plus 2 e to the 2x minus 1 right? And so now we can say that u is equal to e to the x. Therefore, du is equal to e to the x dx. And so we get u plus an e to the 2x is u squared. Yeah, this is going to work great. So 2u squared plus u minus 1. All right, there we go. So this is just a rational function. So let's factor the denominator. So 2u squared plus u minus 1. So 2 times minus 1 is minus 2. So we want to say, if this is going to factor, we want to say 2u squared minus 2u plus, no, that's not going to work, plus 2u minus u minus 1. Yeah. Right, because remember factoring with a leading coefficient, a trinomial, a quadratic trinomial with leading coefficient not 1. You say 2 times the last term, or the leading coefficient times the last term is minus 2, and then you need to add those like this so where you get the middle term, but then you also have this coefficient times this coefficient equals the minus 2. And that means this grouping is going to work. So if we factor out a 2u here, you get u plus 1. Factor out a minus 1 here, u plus 1. Now factor out a u plus 1. And there we go. So we've got 2u minus 1 times u plus 1. Okay, so now we want to write the form of the decomposition. We've got 2 linear factors to the first power. Okay, now we want to multiply the entire equation by the least common denominator to clear the fractions. So we've got 1 is equal to a. Okay, so if u is equal to minus 1, then minus 2 minus 1 is minus 3. So b is equal to minus 1/3. If u is equal to 1/2, then you've got 1/2 plus 1 is 3/2. So 3/2 a. And that's it. So a is equal to 2/3. So a is equal to 2/3 and b is minus 1/3. Okay, so this becomes okay. So with any linear, anytime you've got a constant and then the denominator is a linear factor raised to any power, that you can always do a substitution on that linear factor and get the integral. But these are simple enough. We could do this mentally. So the integral of 1/2u minus 1. So you're going to have natural log of the absolute value of 2u minus 1. And then, but we'd have to have a 1/2 factor there. So we need to say, so this is going to be 1/3. Right, because take the derivative. You get 1/2u minus 1 times the derivative of 2u minus 1, which is 2/3. Plus c. Okay, so now u is equal to e to the x. Okay, but now we can combine these two. And there we go. Okay, so looking at this, we see a root in the denominator. And so, one way, whenever you see a root in the denominator, to me, I think about the fact that when you take the derivative of the square root, it comes 1/2 square root of that. So, it's potential to get to where the du matches something in the denominator. And so if we say, it's actually going to work out pretty well here if we say that u is equal to 1 plus e to the square root of 1 plus e to the x. Okay, and so if we take du dx, so what happens? we get, so the derivative of the square root of something is 1 over 2 square root of that something. Times the derivative of that something. What is the derivative of 1 plus e to the x? That's e to the x. Okay, and so this works out great, right? Because what we have is we multiply both sides by 2 dx. We get right? And look, we've got e to the x over the square root of 1 plus e to the x dx. So this is going to work out great. But you see what I mean, how when you have a root in the denominator, when you take the derivative, you get a root in the denominator. So you can, it's always the potential to where the differential is something in the denominator, but not every time. But okay, but we're going to need x, though. We're going to need x. So how do we get x? If we square both sides of this, okay, now subtract both sides by 1. Now take the natural log of the entire equation. Natural log of e to the x is x. And then we've got natural log of u squared minus 1. Okay. So what we've got is x, which is natural log of u squared minus 1, times 2 du. So 2, and then okay. So can we simplify this anymore? Yes, we can, because remember the natural log of AB is equal to the natural log of A plus the natural log of B, and we can write this as u plus 1 right? So what we have is 2 okay. So what do we do here? Well, okay, so these aren't a problem to solve. And if you think about it, like if we made another substitution, so if we said z is equal to u plus 1, what we're going to get is dz is equal to du, and that just changes it into natural log of z dz. And so these are u plus 1 and u minus 1 are really simple. We can treat them because their derivatives are just the derivative of d, the differential of d of u plus 1 is just du, then we could just do this mentally and treat this as a single variable. So what that means is that okay, but we need to take the integral of the natural log of x. Okay, in the integration by parts section, we determine this integral. You could determine the integral of the natural log of x using integration by parts. And so if we go grab that integral, so look, here's the natural log of x. It was x natural log of x minus x. I'll just write that in. Okay, so again, we would technically make a substitution here, like substitute like z is equal to u plus 1, but we can just, since we see u plus 1, u minus 1 are so simple, and they're not going to result, like we could just assume that this is just a single variable, u plus 1. So in that case, what we've got is, so okay, this integral with the 2 is 2 times the variable natural log of the variable minus, and then 2 times the variable, and then plus c, but we're going to leave out the plus c for now, and so that's it. Okay, now this is 2 times the variable times natural log of the variable minus 2 times the variable, because we have to distribute the 2. Okay, now we can put the plus c. Okay, and that's it. So, okay, and so now before we substitute the u in, let's simplify this. All right, so we've got 2u plus 2 minus 2u minus 2 plus 2u minus 2 minus 2u plus 2, and let me just take off the plus c for now. Okay, so we've got 2u natural log of u plus 1 plus 2 natural log of u plus 1. Okay, and then plus 2u natural log of u minus 1 minus 2 natural log of u minus 1, and then minus 4u. And then the minus 2 plus 2 goes to 0. Okay, so we can combine the 2u natural log of u plus 1 and the 2u natural log of u minus 1. Those are adding together. So we multiply u plus 1 and u minus 1. U plus 1 times u minus 1 is u squared minus 1. So 2u natural log of u squared minus 1. Okay, combining these two logarithms, we get 2 natural log of u plus 1 over u minus 1 minus 4u. Okay, so now let's bring in the u. So we've got 2u is equal to natural log of 1 plus e to the x. All right, natural log of u squared is 1 plus e to the x. 1 plus e to the x minus 1 is just e to the x plus 2 natural log of minus 4. Okay, this is x, so we've got 2x natural log of, or square root of 1 plus e to the x, and then minus 4 plus 2 okay, so we've got 2 times, and then we can factor out a 1 square root of 1 plus e to the x. So 2 square root of 1 plus e to the x, and then it would be x minus 2, and then square root of 1 plus e to the x plus 2 natural log of plus c. And there we go. Okay, so I look at this and I see I think, all right, the derivative of natural log of x plus 1 is like a 1 over the variable inside the natural log. We've got a variable in the denominator here, but it's not an x plus 1, it's an x squared. So, I don't think there's any easy substitution to use here. But just looking at this, I'm thinking integration by parts, because if we say that we have the natural log of u is equal to the natural log of x plus 1, then this gets simplified, I would say. Right? We remove the natural log. We have 1 over x plus 1. And then if we say dv is 1 over x squared dx, this as an integral gets simpler. So the integral of x to the minus 2 is just minus 1 over x. So the derivative and the integral get simpler. So to me, integration by parts should work. All right, so we've got u times v minus the integral of v du. Bring out the plus, and we've got okay, and so yeah, we can solve this. Okay, so we need to split this up into, we need to do partial fraction decomposition on this. All right, so we've got 2 linear factors to the first power. So what this results in is 1 is equal to a. All right, when x is equal to 0, you've got a is equal to 1. When x is equal to minus 1, you've got b is equal to minus 1. So we've got the integral of 1 over x dx minus, right? That's what this integral is. This is 1 over x plus, or 1 over x minus 1 over x plus 1. So natural log of the absolute value of x minus natural log of the absolute value of x plus 1, which is natural log of the absolute value of x over x plus 1. And so there we go. Plus c. And that is the integral. Okay, looking at this, I'm wondering, what is the derivative of arctangent of y? Okay, it's 1 over 1 plus y squared. So we want to say that u is equal to arctangent of y. Therefore, du is equal to 1 plus y squared. Okay. And so making the substitution, we have, so, all right, when y is equal to minus 1, arctangent, or u is equal to minus pi over 4. Okay, when y is equal to 1, u is equal to pi over 4. Okay, so we've got now e to the u du. So this is e to the u, going from pi over 4 to minus pi over 4, e to the pi over 4 minus e to the minus pi over 4. And actually, if you look at the definition of hyperbolic sine is e to the x minus e to the minus x divided by 2. So we could also say that this is 2 hyperbolic sine of pi over 4. Same thing. Okay, so you know, we could do just treat this like an integration of a rational function, but I'm wondering if we could make a substitution. It doesn't look like it. So, okay. Integration of a rational function. The order of the numerator is less than the order of the denominator. Okay, so next step is to fully factor the denominator. So we've got so that's fully factored. Now let's write out the form of the decomposition. We've got a linear factor to the first power and then a quadratic factor to the first power. Okay, now let's solve for A, B, and C. Multiply by the least common denominator. So we've got 2x minus 3 plus bx squared plus cx. So 2x minus 3 ax squared plus 3a plus bx squared plus cx. So we've got 2x minus 3 is equal to a plus b x squared plus cx plus 3a. Okay, so we can see that 3a is equal to minus 3, so a is minus 1. We can see that c is equal to 2, and then a plus b is equal to 0, so a is equal to minus b, so b is equal to 1. So we've got minus 1 plus, and then x plus 2. Okay, and so now we want to integrate this, and we integrate this term here by, we first split this up into two separate integrals. So what we've got is minus the integral of 1 over x dx plus the integral of x squared plus 3 and then x and then plus okay. So this integral is easy. This integral comes from that formula. We have when we simplify it down to 1 over x squared plus a squared, that kind of a form, we have that formula. And this we can do using a substitution. So u is equal to x squared plus 3. So du is 2x dx. So 1/2 du is x dx. So we've got, bring out the 1/2. So 1/2 natural log of the absolute value of u, 1/2 natural log of x squared plus 3. Okay. Okay. This is minus natural log of the absolute value of x. Okay, and then this, we go to this formula. Okay, so a here is, so 2 times a is root 3. So 1 over root 3 inverse tangent of x over root 3. Okay, so we've got and there we go, plus c. Okay, looking at this, I think just saying u is equal to root x and seeing what happens, or maybe multiplying by the conjugate of this. So just curious, what is the... Okay, so this is x minus, and then, okay, so then we just do minus, and then x root x times x root x is x cubed. So yeah, that gets significantly simpler, but then we still have this root x minus x root x in the numerator. Okay, so let's just, when we see a radical, we can always think about substituting, saying like u is equal to that entire radical. So let's do this. U is equal to root x. And so I'm going to go ahead and square both sides and then take the derivative. Okay, so 2u du dx is equal to 1. So 2u du is equal to dx. Okay, so, all right, we've got u plus, now x is u squared. And then dx is 2u du. Yeah, so that's going to work out. And we've got u cubed plus u is just u times u squared plus 1. Is that right? Yeah. Okay. So 2 oh no, it's over 1. Okay, now this is that form, is this form, right? So what we've got is, with a equal to 1, we've got 2 arc tangent of u. Okay, now u is equal to root x, so this is 2 arc tangent root x, and that's it. Okay, so here I'm thinking trig substitution. We have the a squared minus x squared. It's not under a square root. I mean, it kind of is, right? We've got the root 2, but then cubed. So yeah, let's do a trig substitution. So we've got a squared minus x squared. That's this. with a is equal to 2, so we want to say that x is equal to 2 sine theta. Therefore, dx is equal to 2 cosine theta d theta. And so then, all right, well, what's 4 minus x squared? Let's do that first. So 4 minus x squared is 4 minus 4 sine squared theta. Factor out of 4, 1 minus sine squared theta. So this is 4 cosine squared theta. Okay, so 4 cosine squared theta to the 3/2 is what? 4 to the 3/2, and then cosine cubed theta, right? 2 times 3/2 is 3. Now, 4 to the 3/2 power, so the square root of 4 is 2. 2 cubed is 8. So this is 8 cosine cubed theta. All right, that's what 4 minus x squared to the 3/2 is equal to. All right, so we've got 8 cosine cubed theta, and then x squared is 2 sine squared theta, and then dx is 2 cosine theta d theta. All right, so we've got 4 over 8, so 1/2, and then sine squared theta over cosine squared theta is tangent squared theta. Okay, now to solve tangent squared theta, what we want to do is change this to secant squared theta minus 1. And why do we want to do that? Because secant squared theta is great for integration. Okay, so we've got 1/2 minus, all right, what is the integral of secant squared theta? It's just tangent theta. Okay, minus, so we could do okay, so now we've got to convert back to the x domain. Okay, so here's the right triangle, theta. Okay, so what we've got is we defined it as sine theta is equal to x divided by 2. Sine theta is opposite over hypotenuse. Okay, so this side squared plus this side squared is equal to 4. So this is the square root of 4 minus x squared. Therefore, tangent theta is equal to opposite over adjacent. Okay, and theta is equal to, right, we get the definition of just the theta from our definition. Okay, so we've got, we could just say 1/2, let's use this, 1/2, or no, we'll do, so minus plus c. And actually, I messed this up. I didn't square this. This should be 4. And so there is no 1/2 factor. Okay, so we don't have this, don't have this. Okay, here I see this root x, and I think, you know, rationalizing, if we say that u is equal to root x, we could just turn this into strictly powers. Okay, so now we don't want to take the derivative here because we don't have a root x in the denominator. So let's square both sides. Now take the derivative of the entire equation with respect to x. So 2u du dx is equal to 1. So 2u du is equal to dx. Okay, can we need x cubed. Can we get x cubed? So u squared is equal to x. X cubed is equal to u to the 6th. Okay, so 1 plus u to the 6th, root x is u, and then du, or dx, is 2u du. So okay. So now let's solve this, and we see here, we can say that z is equal to u cubed. Therefore, dz is equal to 3u squared du. Therefore, 1/3 dz is equal to u squared du. And so what we've got is, so u squared du, let's take out that 1/3. So u to the 6th is z squared. And then, there we go. Now this is that form, the variable squared plus constant, and so this is arctangent of z. Right? If we look here, see, arctangent of z. Okay, but z is equal to u cubed. But u is equal to root x. So x to the 1/2 cubed is x to the 3/2. So there we go. Okay, so I look at natural log of tangent x, and I think the derivative of that is 1/tangent x. It involves 1/tangent x. And then it also, so this derivative is 1/tangent x times secant squared of x. And so, to me, let's see what that simplifies to. So 1/tangent x is cosine x over sine x. Secant squared x is 1/cosine squared x. And so, oh yeah, there we go. This simplifies to 1/sine x cosine x. So that's it. We want to say that u is equal to the natural log of tangent x. Therefore, du we just saw was that. Okay, and so this becomes just u du. Okay, but when x is pi over 4, natural log of 1 is 0. U is 0. When x is pi over 3, u is natural log of 3 over 2. Okay, so 1/2 u squared with u squared evaluated from 0 to natural log of 3 over 2. So 1/2, and then, so, okay, we just have natural log of 3 squared over 4. So this is 1/8 natural log of 3 squared. Okay, just looking at this, to me, just looks like we need to do integration by parts. I mean, unless, okay, let's see what this does. U is equal to 1 plus x squared. Du is 2x dx. But then we're going to need to, yeah, so let's do, we would need to solve for x, right? So we're going to introduce a radical. So so we have to do integration by parts. We're going to have to make the natural log of 1 plus x squared u, because we can't make it dv because we're trying to find the integral. Okay, and then dv is dx. So v is x. du is 1 over 1 plus x squared times the derivative of 1 plus x squared is 2x. So 2x. Okay, so all right, u times v minus the integral of v du. Just bring out the 2. So let's make this x squared plus 1. Okay, yeah, we can solve this. So let's do, so this is a rational function, but the order of the numerator is equal to the order of the denominator. So let's do polynomial long division to separate this up. Okay, x squared divided by x is 1. Okay, minus 1. So x squared over x squared plus 1 is 1 minus, okay, so this integral is equal to minus, okay, and then plus okay, so we've got minus 2x plus, Okay, here's that form with a is equal to 1. So we've got 2 arctangent x. Okay, so let's simplify. We can factor out an x here. Well, I mean, that's fine. Just gonna leave it like that. Okay, so to me, this just looks like a classic integration by parts. We want to say that u is natural log of x, and then dv is x to the 5th. Well, okay, I'm saying that it's the integration by parts because I can't see a substitution that would work here. And then we can eliminate the natural log with this, with integration by parts, saying that u is equal to natural log of x. And then, yeah, we got to integrate this, but that's not so bad. Where this is dx, right? And so we're going to end up with an easy integral. 1 to 2. So u times v going from 1 to 2 minus the integral of v du. Right? So v du we just get, see? So we've got 1/6. So what is this? Okay, I made this look kind of confusing here. So this is going to be x to the 6th natural log of x. Okay, times 2 to the 6th times natural log of 2, and then minus 0, because natural log of 1 is 0. Okay, minus 1/6. Okay, now again, we've got 1/6, so we can take out the 1/6. X to the 6th evaluated from 1 to 2. Okay, so 6 is 2 times 3. So we've got 2 to the 5th over 3, natural log of 2, minus 1 over 36, 2 to the 6th minus 1. So 2 to the 5th is 32. 2 to the 6th is 64. Okay, 64 divided by 4 is 16. 16 divided by 4, or 36 divided by 4 is 9. Oh, well, no, we want to combine these two. Yeah, minus 60. Okay, wait. This is plus. So minus 64 plus 1 is minus 63 over 36. 9 times 7 is 63. 9 times 4 is 36. And there we go. Okay, so looking at this, it's kind of hard to see because of for some reason, but if you look, what we've got is a first order polynomial in the numerator and a first order polynomial in the denominator. So this is a rational function here, a rational expression. What do we do if we're just solving this using the rational, the partial fraction decomposition method? We first check to see if the order of the numerator is less than the order of the denominator. If it's not, then we do polynomial long division. So let's do that. 12t plus 1. It's hard to see that this is a rational expression because we don't have like a t squared. You know, these are first order polynomials. Okay, then 3t plus 1. All right, 12t divided by 3t is 4. 4 times the divisor, 12t plus 4. 1 minus 4 is minus 3. So what this means is that 1 plus 12t over 1 plus 3t is equal to 4 minus, right? Okay, now this we can solve. So we've got from 0 to 1, 4 minus okay, so with the partial fraction decomposition, any integral with the linear factor, we can always do a u substitution to solve it. But this is simple enough to where we can do this mentally. All right, well, okay, here, this is going to be just 4. Right, because this goes to t, and then t evaluated from 1 to 0 is just 1, so we got 4. And then here, so this integral is natural log, or 1/3 natural log of the absolute value of 3t plus 1. Because the derivative of the natural log of the absolute value of 3t plus 1 is 1 over 3t plus 1 times 3. So we take out the 1/3, and we've just got a 1. And so what we're left with is natural log of the absolute value of 3t plus 1 evaluated from 0 to 1. Okay, so we've got natural log of 4, 2 natural log of 2, minus natural log of 1, which is 0. So we've got 4 minus 2 natural log of 2. Okay, this just looks like the integral of a rational function. We just need to do partial fraction decomposition and do the whole process. So we've already got the denominator is already factored. The order of the numerator is 3. The order of the denominator is 4. It's already factored. We've got these 2 quadratic factors. So the form of the decomposition is, so these quadratic factors to the first power, so we just put ax plus b cx plus d. Okay, now we need to solve for a, b, c, and d. Okay, so we've got 3x cubed minus x squared plus 6x minus 4. And then we've got ax plus b times x squared plus 2 times x squared plus 1. Okay, and so let's just go ahead. I don't see any, if we set x is equal to a certain number, we can't solve for any single variable. So let's just go ahead and distribute everything, distribute and group everything. So ax cubed plus 2ax plus bx squared plus 2b plus cx cubed plus cx plus dx squared plus d. Okay, so we've got a plus c x cubed, and then b plus d x squared, and then 2a plus c x, and then 2b plus d. All right, so a plus c is equal to 3, b plus d is equal to -1, 2a plus c is equal to 6, 2b plus d is equal to -4. Okay. So if we multiply this by 2, we get 2b plus 2d is equal to -2. So if we subtract these two equations, we get d minus 2d minus 4 plus 2. D is equal to 2. If d is equal to 2, then -1 minus 2, then b is equal to -3. If we multiply this equation by 2, we get 2a plus 2c is equal to 6. Subtract these two equations, you get minus c is equal to 0, c is equal to 0, so a is equal to 3. Okay, so we've got 3x minus 3, and then here is just 2. All right. So we've got we could take out a 3 here. We've got x minus 1. Okay. That's what we need to solve. And so to do this, we split this up into two separate integrals. Okay, these we solve using that formula, this formula. This we solve using saying u is equal to x squared plus 1. So that's 1/2 du is x dx, right? So we've got taken out the 1/2, we've got 3/2, and then 1 over u du, 3/2 natural log of the absolute value of u. So 3/2 natural log of the absolute value of x squared plus 1, that's always positive. So, okay. So this is 3/2 natural log of, okay. Now coming to the formula, we've got, this is going to be with a is equal to 1, this integral is arctangent of x. So okay, and then this is, so we've got 2 times 1 over root 2 arctangent of x over root 2. So that's it. And so let's bring this closer here. 3/2 natural log of x squared plus 1. Okay. Well, plus c. And we can simplify this because if 2 over root 2, if you multiply that times root 2 over root 2, that's just root 2. Right? 2 over root 2 is 2 root 2 over 2. Okay, so there you go. Okay, so I see the 1 over x, and I think that the derivative of that is minus 1 over x squared. And yeah, we don't have 1 over x squared, we have 1 over x cubed. But then, so that's 1 over x squared times 1 over x, and we're substituting for 1 over x. So to me, let's definitely see what happens when we do this. Okay, so du is minus 1 over x squared dx. So minus du is 1 over x squared dx. Now, this integral is right. So you've got u cosine u du with a minus sign out front. Okay, we can solve that with integration by parts. So we're going to say that z is equal to u and dp is cosine u du. So dz is du, p is sine of u. So let's just not worry about the negative at the moment. Let's just get this integral. So zp minus the integral of p dz. So this is u sine u. The integral of sine u is cosine u, minus cosine u. All right, so we just need to put the minus sign in front. So we've got minus u sine u minus cosine u, all right? But u is 1 over x. There we go. Okay, so this integral, I played around with it for a little bit to try and find the antiderivative. I put this into the calculator. It doesn't give an answer. So if we say okay, store this as an equation, and then we want to just find the antiderivative. Right, it doesn't give an answer. But if you look at this, so we're not trying to really find an antiderivative as much as we're trying to find this definite integral. In most cases, we need the antiderivative to do this, but if there's some potential trick we can use to get this definite integral, then we want to use that, right? Well, if we look here, we're going from minus pi over 2 to pi over 2, so like minus a to a. And when it comes to definite integrals that are centered about 0 like that, what did we learn? Well, so whenever you see a definite integral that's going from like minus a to a, then one thing you want to do is check, do you have an even or an odd function? Okay, so let's do that. If we take this function and put in minus x, we get minus the function. So f of minus x is equal to minus f of x. This is an odd function. Okay, and so since this is an odd function, we know this is going to be 0. Because definite integrals are like areas under curves, right? If you have an odd function, it's symmetric about the origin. So anytime you're integrating from minus a to a, somewhere centered about the origin, the areas are always going to cancel each other out. If it was an even function, then what we do is we take out a 2 and we change this lower limit to 0. But this is an odd function, so that means that this integral is equal to 0. Okay, so here I see the x squared minus 1 squared and under a square root, so a trig substitution always comes to mind. You know, but potentially you think, well, if we said that u is equal to this entire radical, would that potentially help us? But what's going to happen is we're just going to get another radical over here. So let's just go ahead and do the trig substitution. That should simplify this a good bit. All right, so we've got x squared minus 1 squared. So a is 1, so we want to say that x is equal to secant theta. All right, therefore dx is equal to secant theta tangent theta d theta. All right, so the square root of x squared minus 1 is secant squared, the square root of secant squared theta minus 1, which is the square root of tangent squared theta, which is just tangent theta. Okay, so we've got the integral of the natural log of secant theta plus tangent theta, and then dx is secant theta tangent theta d theta. Okay, so now let's go ahead and do integration by parts, because I see we can say that if we say dv is secant theta tangent theta d theta, then v is secant theta, and then if we say u is natural log then du is, so 1 over secant theta tangent theta, and then we have secant theta tangent theta plus secant squared theta right? So 1 over secant theta tangent theta plus the derivative of secant theta plus tangent theta, times the derivative of secant theta plus tangent theta, which is this. Okay, now let's see. All right, if we take out a secant theta, then we've got secant theta plus tangent theta. So this is secant theta. All right. So the integral is u times v minus the integral of v du. Well, yeah, this will have a d theta. So there we go. But now we need to draw the right triangle because we need to convert back to x. Okay, so we've got secant theta is x, so that means that cosine theta is 1 over x. Cosine is adjacent over hypotenuse, so that means this side is the square root of x squared minus 1. Okay, so we've got secant, we just need tangent. Tangent theta is adjacent, or opposite over adjacent. Okay, so secant theta is x, and then x plus, okay, minus, there we go. Okay, so if we think about the way we learned how to do solve trigonometric functions, here, you know, it's not a product of a secants and tangents, but we use the exact same concepts to try and figure out how to solve an integral like this. So what we do is we say that this, we can solve it. Why is that? Because we've got an even power on the secant, but then it's not in the denominator to where, so we've got an even power that we can do this. We can say, and then, and so because we have an even power on the secant, that means we can take out a secant squared theta d theta, and then we're still left with an even power on the secant, and because of that, we can change this into purely a function of tangent. Right, so what is secant squared theta? That's tangent squared theta plus 1. So we've got tangent squared theta plus 1 times tangent squared theta plus 1 all over tangent squared theta secant squared theta d theta. And so now what we can do is we can say that u is equal to tangent theta, therefore du is equal to secant squared theta d theta. And so we get and there we go. And so now, you know, we can solve this. It's not the easiest, but we can solve it. So, you know, this is definitely solvable. Well, because we know it's a rational function, but then we've got this single term in the denominator, so we can separate this out. You know, it's a lot more complicated if you've got this in the denominator. But so, okay, what do we do? If we want to separate this out into separate integrals, let's expand this. U to the fourth plus 2u squared plus 1 over u squared. So this is u squared plus 2 plus, right? So we can just do this by in our heads here. So 1/3 u cubed plus 2u minus 1 over u plus c. Okay, u is tangent theta, so 1/3 tangent cubed theta plus 2 tangent theta plus there we go. Okay, just looking at this, I think about cotangent is cosine over sine. So I just wonder if we multiply this times 1 in the form of sine over sine, does that do anything? So if we multiply this times, so we get sine x plus 4 cosine x, and then 4 sine x minus cosine x. And then if we make a substitution, so yeah, if we said that u, so let's say there was no 4's here, then we could say u is equal to sine x minus cosine x, and we would get du is equal to sine x plus cosine x dx. And so I'm wondering if we could somehow make something like that work. So if we said u is equal to 4 sine of x minus cosine of x, then du is 4 cosine x plus sine of x. Yeah, there we go. Okay. dx. And so that's this. All right, so this integral is four sine of x minus cosine of x, and then sine of x plus 4 cosine of x dx. Okay, and so if we make the substitution again, that u is equal to 4 sine x minus cosine x, then du is 4 cosine of x plus sine of x dx. Okay, and so, all right, now when x is equal to pi over 4, we've got sine of pi over 4 times 4 minus cosine of pi over 4. Then u is 3 root 2 over 2. All right, when x is pi over 2, then u is, cosine pi over 2 is 0, so then u is 4. Okay, and then we've got 1 over u du. So this is the natural log of the absolute value of u evaluated from 3 root 2 over 2 to 4. So the natural log of 4 minus the natural log of 3 root 2 over 2. So 4 is 2 squared, so we can say 2 natural log of 2 minus natural log of 3 root 2 minus natural log of 2. Okay, so 2 natural log of 2 minus natural log of 3 plus natural log of root 2 minus natural log of 2. Okay, 2 natural log of 2 minus natural log of 3. This is 2 to the 1/2, so all right, so 2 natural log of 2 minus natural log of 3 minus 1/2 natural log of 2 plus natural log of 2. So we've got 2 minus 1/2 is 3/2. 3/2 plus 1 is 5/2. So 5/2 natural log of 2 minus natural log of 3. There we go. Okay, so just looking at this, to me, we see this radical here, and so if we go ahead and substitute u is equal to this entire radical, we should be able to get rid of radicals. There's a good chance. So, right, that's the whole idea of rationalizing. You a lot of times when you substitute any radical with the entire expression for it, say that a variable is equal to that, then you can the way you can simplify it and get rid of the radicals and just have powers, which is much easier to work with. So, all right. Now, you make a choice. At this step, you make a choice. Do you differentiate right here, or do you square both sides and then do implicit differentiation? Here, we're going to go ahead and differentiate at this step because in the integrand, we've got this radical in the denominator. And so we know when we differentiate, we're going to get this in the denominator. So let's do it that way, right? It's 1, the derivative of the square root of something is 1 over 2 times the square root of that something, and then times the derivative of that something. So we got 1 plus the derivative of x to the 3/2 is 3/2 x to the 1/2. Okay. And so, I mean, this still might not work out. This is pretty ugly. We'll see. We might have to go back and try something else. But so, okay, what do we have? We've got, so 1 plus 3/2, we'll say root x, two du is equal to the entire integrand. Okay. So what is root x? We need root x. So if we square both sides here, we get x plus x to the 3/2 is equal to u squared. I don't know how well this is going to work out. Yeah, I'm not sure if we can solve for a square root of x here. If we factored out a root x, you get x to the 1/2 plus x. Yeah, so, okay. That didn't work out. So now I want to try just saying x, or u is equal to x to the 3/2, which x to the 3/2 is x root x, right? X cubed, the square root of x cubed is x root x. So if we say u is equal to x root x, then now I'm going to say let's just square both sides here. So this is x. So this is x cubed. All right. And so dx of the entire equation, you've got 2u du dx is 3x squared. So 2u du over 3x squared is equal to dx. Okay, so let's see. If we come here, we can factor out, let's say, an x, and we get 1 plus root x. Right? So this is root x. There we go. Okay. Yeah. So this is going to work, or should work, I think, because, okay. So this we can write as root x okay, and so now if we say that u is equal to, we could say 1 plus root x, then du is 1 over 2 root x dx. So 2 du is, okay, and so with that, take out the 2. 1 plus, we've got 1 over root u du. So we've got 2 times minus 1/2 plus 1. So this is just root u. So u is 1 plus root x. So there we go. Oh, wait. No. This becomes 4. 2 divided by 1/2 is 4. Okay. All right. So this looks like a simple trigonometric integral. We need to have, we're looking for the odd power. So we see sine cubed, and so what that means is what we're going to do, we're going to take out a sign from this. Okay, and so now what we can then do is we can, the sine squared theta is 1 minus cosine squared theta. So we've got this sine theta d theta, and then the rest is a function just of cosine theta, which allows us to say that u is equal to, or u is equal to cosine theta. Therefore, du is minus sine theta d theta, so minus du is sine theta d theta. All right? When theta is equal to 0, u is equal to 1, cosine 0 is 1. When theta is equal to pi over 2, cosine of pi over 2 is 0. All right? And so take out this minus sign, and we've got 1 minus u squared du. So we've got, we could do this. We could say, bring the minus sign in and get u squared minus 1 and so, I mean, we could do, if you know, actually what we could do is just another way of looking at this. We could say, and remove the minus sign, right? And so now we just got 1 minus u squared times u squared, and that's u squared minus u to the 4th. All right, so 1/3 u cubed minus 1/5 u to the 5th, evaluated from 0 to 1. And so when you plug in 0, this is 0, so it's just plugging in 1, 1/3 minus 1/5. 5 over 5 times 1/3 is 5 over 15. 3 over 3 times 1/5 is 3 over 15. So 2 over 15. All right, so looking at this, this is a like 1 squared minus like e to the minus x squared. So it's like it's something that's kind of like an a squared minus x squared. So we can always potentially think about a trig substitution, maybe. However, I don't know, but I'm just thinking to do this and see what happens. Because what we're going to get, du is 2 right, and then times the derivative of this. So okay, derivative of 1 minus e to the minus 2x, it's going to be 2e to the minus 2x. So 2e to the minus 2x, the 2's cancel. Okay, and so, but we still need an e to the x. So, all right, well, what is e to the minus 2x? So you square both sides. Let's see what happens. Square both sides. So e to the minus 2x is 1 minus u squared. So if you divide e to the minus 2x by both sides here, you get du over 1 minus u squared is equal to which is nice, but we still have this e to the minus x. E to the minus x, if we raise both sides of this to the 1/2 power, we get e to the minus x is, all right, so let's see what happens here. E to the minus x, and then just dx over the square root of 1 minus x squared, so that's to the first power, so 1/2 minus 1, what we get is that's not bad. That's pretty I would say that's pretty simplified. Yeah, because now we can solve this with a trig substitution. Okay, so we've got a squared minus x minus the variable squared. So we want to say that x is equal to sine theta. So u is equal to sine theta. Therefore, du is cosine theta d theta. Square root of 1 minus u squared is 1 minus sine squared theta is cosine squared theta. So this is cosine theta. All right. So we've got 1 over cosine theta times cosine theta d theta, which is just, okay. So what is theta? Theta is inverse sine of u. But what is u? U is square root of 1 minus e to the minus 2x. There we go. Okay, so looking at this, the first thing I think about is that if we change from tangent squared theta to secant squared theta seems a lot nicer to have in an integrand because the derivative of tangent theta is secant squared theta. So I feel like let's just go ahead and do that. So tangent squared theta is secant squared theta minus 1. So theta secant squared theta d theta minus, okay, so to me this is yeah, we kind of made it more complicated visually, but I'd rather be working with this. All right, so we've got theta secant squared theta d theta minus 1/2 theta squared. Okay, now here let's do integration by parts. And so we can say dv is secant squared theta d theta, right? So v is tangent theta. U is equal to theta, so du is d theta. So theta secant squared theta d theta is u times v minus the integral of v du. Okay, let's go to our table of integrals. The integral of tangent theta is natural log of the absolute value of secant theta. Okay, and so we've got this entire integral is theta tangent theta minus natural log of the absolute value of secant theta minus 1/2 theta squared. And I guess that's it. Yeah. Okay, so this looks just like a integration of a rational function. So the order of the numerator is less than the order of the denominator. So now we want to factor the denominator. We've got the difference of two squares here, x squared squared and 4 squared. Okay, so now we've got another difference of squares. There we go. That's fully factored. So now let's do partial fraction decomposition on this. So we've got two linear factors and a quadratic factor, both or all three are raised to the first power. So we're done with x plus 2. Okay, we're done with the x minus 2 factor, and now we're done with the x squared plus 4. Now let's clear the fractions, multiply by the least common denominator. All right, so we've got 1 is equal to a times, okay, plus b okay, plus okay, so now let's say, what if we set x equal to 2? Then we've got we're left with this term, so that's 4 times 4 plus 4 is 8. 8 times 4 is 32. So 32b is equal to 1. B is equal to 1 divided by 32. All right, what if we set x equal to minus 2? Then these two terms go away, and we're left with a times, so this is going to be 8 times minus 4, so minus 32a is equal to 1. A is minus 1 over 32. Okay. So now, what if we set, I guess there's no more, we can't eliminate factors. So, okay. We're going to have to just get 2 more equations. So if we set x equal to 0, what happens? We get 4 times minus 2 is minus 8. Minus 8 times minus 1 over 32 is 1 over 4. Okay. Here we have 4 times 2 is 8. 8 times 1 over 32 is 1 over 4. Okay, plus, all right, now we've got D, the C goes away, and then we've got 2 minus 2. So 1 is equal to 1/2 minus 4D. So minus 4D is equal to 1/2. So D is equal to minus 1/8. Okay. Now, if x is equal to 1, we've got, so 1 is equal to, then 5 times minus 1 is minus 5. Minus 5 times minus 1 over 32 is just 5 over 32. Okay. Here we've got 5 times 3 is 15. 15 times 1 over 32 is 15 over 32. All right. Then we've got C minus 1/8. And then 3 and minus 1. Okay. 20 over 32 is what? 10 over 16, 5/8. Okay. Plus, and then, all right, so, well, let's, minus 3 times C, so minus 3C, and then minus 3 times minus 1/8, so plus 3/8. All right. 5, 6, 7, 8. So 1 minus 3C is equal to 1. Minus 3C is equal to 0. C is equal to 0. Okay. So minus 1 over 32. 1 over 32, and then minus 1 over 8. All right, so this integral is equal to minus 1 over 32 plus minus okay, so minus 1 over 32 natural log of the absolute value of x plus 2 plus 1 over 32 natural log of the absolute value of x minus 2 minus 1/8. Okay, so this is that form. We want to use this here. Okay, x squared plus a squared, so a is 2. So we got 1 over 2 inverse tangent of x over 2. So 1 over 2, we're going to have 1 over 16. Okay, so 1 over 16. And then x over 2. Okay, but we can go a little bit further because we can say 1 over 32 natural log of the absolute value of, combine these two logarithms. So x minus 2, all right, minus and there we go. Okay, looking at this, to me, it seems evident that we want to do this for two reasons. Because one, you know, we can, the idea of rationalizing, we can get rid of this radical, but then, so we're not going to take the derivative here. We're first going to say u squared is equal to e to the x minus 1, but we're going to get a derivative that's probably going to involve like an e to the x dx, and we have that. So to me, this is going to work fine. So 2u du dx is equal to e to the x. So 2u du is equal to e to the x dx. See? So we have that. Now we're going to need an e to the x, and we see that e to the x from here is u squared plus 1. So this should work out fine. Okay. We've got u squared plus 1 plus 8. Then we have an e to the x dx is 2u du, and then we have the square root of e to the x minus 1, which is just u. So let's see, did we get that right? We have e to the x dx, that's 2u du. Okay, we have e to the x plus 8, u squared plus 1 plus 8. And then we're left, the only thing we have to replace is the square root of e to the x minus 1 is u. Okay. But now, okay, when x is equal to 0, u is equal to 0. When x is equal to the natural log of 10, e to the natural log of 10 is 10. 10 minus 1 is 9. Square root of 9 is 3. All right, so we've got 0 to 3. U squared plus 9. Let's take out the 2. U squared du. All right. So we can, so we've got, okay, this is a rational function. The order of the numerator is the same as the order of the denominator. So let's do polynomial long division. All right, u squared divided by u squared is 1. Multiply 1 times the divisor. Okay, so we've got this is equal to 1 minus Okay, so we've got okay, and then okay. So this is going to be just this is 3, so 6, and then 18 times, okay, this, what is this integral? 1 over u squared plus 9. We come back to this formula. This is, with a is equal to 3, it's 1/3 inverse tangent of u over 3. So let's take out the 1/3. 18 divided by 3 is 6. So zero to 3. Okay, so 6 minus 6. And then inverse tangent of 0 is just 0, so this is just going to be inverse tangent of 1. Inverse tangent of 1 is pi over 4. So 6 minus 3 pi over 2. Okay, so looking at this, this just looks like a regular rational function. We could solve this using techniques, the process for the integration of a rational function. But just curious, since the order of the numerator is 1 less than the order of the denominator, let's just see if we said u is 9x squared plus 6x plus 5, then we know that when we take the derivative, the order of du is going to be the same order as the numerator. Okay, so factoring out a 6. No, so 3x plus 1 dx is close, but it's not. That's not going to work. So okay, let's just integrate this as a using the techniques of the technique of integration of a rational function. So first step, the order of the numerator is less than the order of the denominator. Okay, so we're not going to have to do polynomial long division. Then next, we want to fully factor the denominator. Now this is already a quadratic factor, right? We have a single quadratic factor to the first power. So, you know, ax squared plus bx plus c. A is 9, b is 6, c is 5. But we still might be able to factor this. And how do you check if you can factor you can check to see if you can factor a quadratic factor by looking at the discriminant. So b squared minus 4 times a times c, 20 times 9. Okay, this is going to be negative. So since it's negative, we know we can't factor it any further. Okay, so what do we do then? Well, okay, well what we just saw is that this is been fully decomposed. And so this is one of the 4 we learned. For a fully decomposed rational function, there's going to be one of 4 terms, and we know how to integrate all 4 of those terms. Again, we have a quadratic factor to the first power, and then we've got ax plus b, with a is equal to 1 and b is equal to 1. Right? So we know how to integrate this. How do we integrate it? Well, the first thing you do is you split it up into two separate integrals. Okay, now this one, usually if the quadratic is simple enough, we could just say u is, make a u substitution, then u is equal to the quadratic, and since we have an x dx here, then it's an easy substitution. But this is a little more of a complicated quadratic, and so the general idea is what you do is we need to get these denominators into the form of like x squared plus a squared type form. That's what's going to allow us to better work with them to integrate. So that's in general what we do. And so we need to complete the square on these two, but on the two denominators. But however, the leading coefficient is 9, is not 1. So what we're going to go ahead and do is we're going to say that let's make a substitution that, and we can do this on both of these at the same time. U is equal to 3x. So therefore, u squared is 9x squared, and 2u is 6x, right? And so therefore, 1/3 du is dx. Okay, so we've got u squared plus 2u plus 5, and then x is equal to 1/3 u. Okay, dx is 1/3 du, and so we have a 1/3, so we can say 1/9 u. Okay. Plus u squared plus 2u, and then this will be a, we'll put this 1/3, yeah, we can bring the, okay, let's bring this 1/9 out. So like that. Okay, so now let's complete the square on the denominator. So x plus a squared is x squared plus 2ax plus a squared. And so we've got 2a is equal to 2, so a is equal to 1. And so u squared plus 2u plus 1 plus 5 minus 1. Okay, we haven't changed this expression. And so, but what we have now is u plus 1 squared plus 4. Okay, so we've got u plus 1 u plus 1 okay. So next what we want to do is we want to make another substitution and say that z is equal to u plus 1. Therefore, dz is equal to du. So we've got u is equal to z minus 1, and then okay, and now we want to split this up into two separate integrals. Okay, now these are the same integral, so we can do minus 1/9 plus 1/3. So minus 1/9 plus 3/9 is positive 2/9. So okay, so Now we can integrate this by saying that P is equal to z squared plus 4. Therefore, 1/2 dp is equal to z dz. So we've got 1/9. Well, okay, bring out the 1/2. So 1/18 1 over p dp. 1/18 natural log of the absolute value of p. 1/18 natural log of the absolute value of z squared plus 4. Okay. So 1/18 Okay, now here we need to use this formula with a is equal to 2. So 2/9 times 1/2 is 1/9. Okay, so we've got, this becomes 1/9 arctangent of z over 2. Okay, but z, what is z equal to? Z is equal to u plus 1. And so u plus 1 squared plus 4 is u squared plus 2u plus 5. Okay. Okay, but u is equal to 3x. And so when we plug in 3x, we get this 9x squared plus 6x plus 5. And that is it. Okay, looking at this, it's just we have a rational function with a linear factor to the second power. And so we could do partial fraction decomposition, but if we do u is equal to x plus 1, then we should flip-flop this, which would allow us, so we could do this, and it would flip-flop it in the sense that we'd have like a u plus 1 squared in the numerator and then just a u squared in the denominator, and so then we could split this all up into separate integrals. But we could also do the partial fraction decomposition, so let's do that. Why not? So the order of the numerator is less than the order of the denominator. Then you want to fully factor this, and this is fully factored, and so we've got, now we want to write the form of the decomposition. Which is that. Now clear the fractions. Okay, so we've got x is equal to, so when x is equal to minus 1, you've got b is equal to minus 1. When x is equal to 0, you've got a minus 1 is equal to 0, so a is equal to 1. So what we have is, this is 1, and then this is minus 1. So we've got okay, so evaluated from 1 to 2, and then this would be just right. So you've got natural log of the absolute value of 1 or 2 plus 1, natural log of 3 minus natural log of 2 plus 1/3 minus 1/2. Okay, 1/3 minus 1/2 is 2/6 minus 3/6 is minus 1/6. Okay, here I can see if we just say u is equal to root t, then that's going to work well, because then du is 1 over 2 root t dt, so 2 du is, right? And so what we've got is, so okay, when t is equal to 1, u is equal to 1. When t is equal to 4, u is equal to 2. And then we've got e to the u, and then times 2 du. So we've got, this just ends up being e to the u evaluated from 1 to 2, 2e squared minus e. Okay, so I see the secant x tangent x, and I know that that's the derivative of secant x. And then with the x here, I'm thinking integration by parts. And so we could say that u is equal to x, and dv is secant x tangent x dx, and therefore v is secant x. And so du is dx. And so this is going to work great. So we've got x secant x tangent x dx is equal to u times v minus the integral of v du. All right, what is the integral of secant x dx? Let's go to our table of integrals. Natural log of the absolute value of secant x plus tangent x. Plus c. There we go. Okay, so looking at this, the first thing I think is we can split this up into separate integrals. Okay, and we know that there's a property of logarithms. If you have a over b to the x power, this is, right? And so we could just go in reverse. And so what we've got is, this is 4 divided by 2. This is just 2 to the x. And then 10 divided by 2, this is 5 to the x. So now integrating exponentials is easy, because, okay, we're going to have 2 to the x over natural log of 2 plus 5 to the x over natural log of 5. Why? Why is that? Because what's the derivative of 2 to the x? What is the derivative of this? It's 2 to the x times natural log of 2 divided by natural log of 2. So you're just left with 2 to the x. See? So that is the integral. Okay, just looking at this, I feel like we just need to do integration by parts. You know, we can say we could potentially make a substitution that u is equal to root x, but, you know, because, okay, the arc tangent, okay, let's see. If we said u is equal to root x, then u squared is equal to x. And so 2u du is equal to dx. And so what we have is arc tangent of u arc tangent of u. I guess that does work. That's okay. That's actually a good substitution. Let's see. U is equal to root x. U squared is equal to x. So 2u du dx is equal to 1. So 2u du is equal to dx. Make the substitution. Arc tangent of u. And then dx is 2u du. Yeah, okay. And so now we can do, just focusing on this, we're going to say that we'll say that, we'll say that z is equal to arc tangent of u, and dp is equal to u du, because I don't want to integrate arc tangent. So dz is equal to, so 1 over 1 plus u squared. du, and p is equal to 1/2 u squared. So u arc tangent u is equal to z times p minus the integral of p dz. So take out the 1/2. So u squared plus 1 okay. So we can separate this up into two fractions. We could do, so polynomial long division, u squared plus 0u plus 0, and then u squared plus 0u plus 1. U squared divided by u squared is 1. U squared plus 0u plus 1. So we've got, this is the splitting this up, we've got, all right, so u squared plus 1 over u, or under u squared is 1 minus okay, so we've got the integral of du minus the integral okay, so 1/2 u squared minus 1/2 u plus 1/2, and then what is this? This is just arc tangent of u, right? 1 over 1 plus u squared. Okay, but now if we multiply this by 2, just the 1/2s go away. So what we've got is u squared okay, but u is equal to root x. So we got x arc tangent of root x minus root x plus arc tangent of root x. So factoring out an arc tangent of root x, you've got x plus 1 arc tangent of root x plus c. Okay, so this should be an easy one. We've got or maybe not. So we're looking for an even power on a secant, which we don't have, or an odd power on the tangent, which we do have. So yeah, that we can do this no problem. With the odd power on the tangent, what we're going to do is we're going to take out a single tangent, and then take out a single secant. And so we will have secant theta, tangent theta, d theta. Okay, and so why do we want to do this? Because then we want to transform the tangent to the fourth theta to secant, just a secant. Secant squared theta, or no, tangent squared theta is secant squared theta minus 1. So we've got secant squared theta minus 1. Secant squared theta minus 1. Secant squared theta. And so what can we do with this? Well, now we can say that u is equal to secant theta. Therefore, du is secant theta tangent theta d theta. And so what we've got is okay, and so let's distribute all of this. We've got, so we'll have a u squared out front, then u to the fourth minus 2u squared plus 1. So u to the sixth minus 2u to the fourth plus u squared. Okay, and so 1/7 u to the seventh minus 2/5 u to the fifth plus 1/3 u cubed. 1/7, so u is equal to secant theta, so 1/7 secant theta to the seventh minus 2/5 secant plus 1/3 okay, so just looking at this, if we said that u is equal to e to the 2x, then u squared is e to the 4x. All right. du is 2 e to the 2x dx. So 1/2 du is e to the 2x dx. Okay, and so this should work. We get 1 plus u squared and then du. Yeah. Okay, and we know that this is arctangent x just from this formula. Right? This is okay plus c, but u is e to the 2x. And there we go, that's it. Okay, so we see we're dealing with an absolute value here. And so remember, with an absolute value, the way every time you see an absolute value in any kind of problem, the way you're looking at it is you're either going to identify which region of the input variable you're working in for that problem, because that's how you simplify an absolute value. If you can identify that you're in like a negative x domain or a positive x domain, then you can simplify the absolute value. And so with a definite integral, that's how we see where we're at based on the limits of integration. Now, if it was an indefinite integral, so just a general antiderivative, I don't think absolute values are that simple. Don't quote me on this, but unless it's a special case, kind of like the natural log, where it happens to be like the derivative of the natural log is kind of independent of the absolute value, then in an antiderivative involving an absolute value, you'd have to give two antiderivatives, right? Depending on, like you would say, the antiderivative is this when x is less than this value, and the antiderivative is this when x is greater than this value. That's the only way you could specify an integral involving an absolute value. Again, unless it's a special case like the natural log, where the derivative and integrals are kind of independent of that. So, but we're not doing an antiderivative here. We're doing a definite integral. And so what we're going to do is we're going to break this up into, we're going to take so we know based on properties of definite integrals, if you're taking the definite integral from a to c of a function, then that's equal to right? And so we're gonna go from -1 to 0, and then from 0 to 2, so that we know we know if the x is negative or positive. Now, the e to the x, if you graph e to the x for all x is always greater than 0. And so if this was happen to be a +1, then we can just remove the absolute value because this is never negative. But it's -1, so what we want to do is first, well, actually, we're not going to go from -1 to 0. We have to see what the crossover point is. So we need to solve for when is e to the x -1, when is that equal to 0? Okay, that's going to be the crossover point, and we'll check it. So we've got, so this is x, and then what is the natural log of 1? E to what power is equal to 1? Well, it happens to be 0. So, right, when x is equal to 0, this is 0. Could have just visually figured that out. Okay, and we can actually take a look at the graph of e to the x -1. And there you go. So it's going to be negative when x is less than 0, and positive when x is greater than 0. All right, so with that, we can write the integral. So from -1 to 0. Now, how do we simplify the absolute value in this region? Well, we know that this is going to be negative, e to the x -1. But because of the absolute value, we're going to return the positive. So we just we say, right? And that's the same thing as what the absolute value would output. So that's 1 minus e to the x. Okay? And then add to that, and we're going to go from 0 to 2. We know e to the x -1 is positive in this region, so we just remove the absolute value. It's just going to be positive. We don't need an absolute value, you see? Okay, so we've got x minus e to the x evaluated from -1 to 0 plus e to the x minus x evaluated from 0 to 2. Okay, so -1 minus 1 over e. Okay. Or no. We start with 0, so okay. 0 minus e to the 0 is 1 minus minus 1 over e plus e squared minus 2 minus e to the 0. So, okay. Minus 1 and then plus 1 over e plus e squared minus 2 minus 1. Okay, 1 over e plus e squared minus 3. So we'll say e squared minus 1 over e minus 3. Okay, so here I see that radical, and well, we could do integration by parts. Let's go ahead and remove the radical. See if this helps to remove the radical. All right, so u squared is y. Take the derivative of all of this with respect to x. 2u du dx is equal to 1. Or wait, no. We're in terms of y here. u du dy is equal to 1. So 2u du is equal to dy. Okay, and so we've got u natural log of u squared times 2u du. And then when y is equal to 1, u is equal to 1. When y is equal to 4, u is equal to 2. So u squared natural log of u squared du. And so I know that natural log of u squared you could write as natural log of u plus natural log of u, right? Because okay, and so you've got u squared natural log of u okay, and so in that case we can add these two, and so what you get is this is 4 okay, and yeah, so let's do integration by parts on this. So we've got okay, so we want to say that let's say that we want to say u is equal to natural log of u, because I don't want to integrate natural log. dv is u squared du. So du is, okay, no, what am I doing? Z, you can't use u. Z is natural log of u. dp is u squared du. So dz is 1 over u du. P is 1/3 u cubed. So from 1 to 2, z times p, 1/3 u cubed, natural log of u evaluated, minus, and then take out the 1/3, u cubed over 3. Okay, so we've got 1/3 times 2 cubed, so 8/3 natural log of 2 minus, and then natural log of 1 is 0. Okay, 1/3, and then 1/3 u cubed, so 1/9, and then u cubed evaluated from 1 to 2. So 8/3 natural log of 2 minus 1/9, 8 minus 1. So 7/9. Okay, but now we need to multiply that times 4. So 32 over 3 natural log of 2 minus 28 over 9. Okay, so, I see that root x, and I'm just thinking, let's go ahead and do this. We can get rid of the radicals. And then, yeah, we have a root x in the denominator, but it's not by itself. So let's go ahead and say that u squared is equal to x. So 2u du dx is equal to 1. 2u du is equal to dx. Okay, x is equal to u squared plus, and then u squared times u cubed, and then dx is 2u du. So we've got, take out a u squared, okay, so let's see if we can just do this visually. Okay, so if we just put ones, then you get u plus 1. Yeah, that would be it with a u plus 1 minus u. Yeah. Okay, so we've got so this is okay, and that is 2 so 2 root x plus 1, and that is it. Okay, so just looking at this, worst case scenario, we just expand this and create separate integrals. Okay, and then when it comes to cosine of 2x, we've got, cosine 2x here, or no, yeah, cosine 2x here. So let's grab these. Okay, so let's just go ahead and expand this out. So cosine squared x plus 2 sine x cosine x, which we know is sine of 2x, plus sine squared x cosine 2x dx. Now sine squared x is 1 minus cosine squared x, so cosine squared x is 1 minus sine squared x, and so to me it seems like we want to go ahead and do that because then we can eliminate terms. But which one? I guess it doesn't matter. So let's just change cosine squared x to 1 minus sine squared x. Okay. So 1 plus 2 sine x cosine x cosine 2x. Now this is, we know this is 2 sine x cosine x is sine 2x. Okay. And so this is so yeah, we could solve that. Perfect. Okay, so this first one is 1/2 sine 2x. That's easy. So let's go ahead and we can just replace it. Okay, here we're just going to say that u is equal to sine 2x. Therefore, du is 2 cosine 2x dx. Therefore, 1/2 du is cosine 2x dx. And so u du. 1/4 u squared 1/4 sine squared of 2x. There we go. Okay, just looking at this, I'm thinking integration by parts because we can differentiate arctangent x, and then 1 over x squared, kind of it reduces when you integrate it. Right? It becomes, okay, and then arctangent of x, the derivative is 1 over 1 plus x squared. Okay. All right, u times v minus v du. So okay, so we can, this is just a rational function. Let's do partial fraction decomposition. We've got a linear factor to the first power and a quadratic factor to the first power. Now let's clear the fractions. Okay, so we've got 1 is equal to Okay, so we've got ax squared plus a plus bx squared plus cx. So a plus bx squared plus cx plus a. So a is equal to 1, c is equal to 0, and since a plus b is equal to 0, then b is equal to minus 1. So we've got okay, so okay. Okay, now we can do a substitution here. If we said that p is equal to x squared plus 1, then 1/2 p is x dx. So what you get is okay, but x squared plus 1 is always positive, so we can remove the absolute value. Okay, so that's this integral here. So we've got and there you go. Okay, so looking at this, it looks like we have an x squared minus a squared type expression, but it's both of these have variables, so we can't think about a trig substitution here. And so what we're going to do is we can, so the x squared minus 4x can be written as x and then x minus 4, right? And so we can write that as the square root of x okay. Now what we want to do is say that u is equal to the square root of x minus 4. Therefore, du dx is 1/2 square root of x minus 4. Okay, so 2 du okay, so now if we make the substitution, we've got the dx over the square root of x minus 4 is 2 du. Right, but now we just need to replace the 1/root x. So we need an expression for, well, we can start by getting an expression for root x. So, okay, we square both sides here. Okay, now add 4 to both sides. Now take the square root of both sides. There's root x, but we have 1/root x. So okay, we can work with this. We can do a trig substitution here. Okay, we've got variable squared plus constant squared. So a is equal to 2. So we want to say that u is equal to 2 tangent theta. Therefore, du is equal to 2 secant squared theta d theta. Okay, and so just to save some room here, let's do let's come up here. The square root of u squared plus 4 is, so u squared is 4 tangent squared theta plus 4. Factor out of 4 tangent squared theta plus 1. Tangent squared theta plus 1 is secant squared theta. So this is 2 secant theta. Okay, so now we make the substitution. The square root of u squared plus 4 is 2 secant theta. Okay, then du is 2 secant squared theta d theta. We're left with, okay, what is the integral of secant theta? We come to our table of integrals. The integral of secant theta is natural log of the absolute value of secant theta plus tangent theta. Okay. But now we need to go back to the u variable. Okay, we said that tangent theta is equal to u divided by 2. So tangent is opposite over adjacent. Okay, the hypotenuse squared is equal to the square root of u squared plus 2 squared. Okay, so secant theta, we need a secant theta. So secant is 1 over cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Okay, so we've got 2 natural log of the absolute value of these two. You get u plus okay, but we can simplify this because this is 2 natural log of u plus the square root of u squared plus 4 minus 2 natural log of 2. We can combine these into one constant. Okay, but u is equal to the square root of x minus the square root of x minus 4. Okay, u squared is equal to x minus 4. X minus 4 plus 4 is just x, so this is the square root of x. And that is the integral. Okay, so I look at this and I think trig substitution, unless we could potentially say that u is equal to 4x squared plus 1, but we don't have an x dx. If we had an x up here, then we would consider that. So, okay, but we can't, how do we do the trig substitution here? Well, if we say that u is equal to 2x, then u squared is equal to what? 4x squared. So what we've got under here is a u squared plus 1, variable squared plus 1. Variable squared plus constant squared is this option. So we want to say that the variable is equal to tangent theta. So we want to say that u is equal to tangent theta. But u is equal to 2x. Therefore, the substitution we want to make is that x is equal to 1/2 tangent theta. Therefore, dx is equal to 1/2 secant squared theta d theta. Okay, so the square root of 4x squared plus 1 is equal to 4 times x squared so this is tangent squared theta plus 1 is secant squared theta so square root of 4x squared plus 1 is secant theta. Okay, so all right, x is 1/2 tangent theta. Square root of 4x squared plus 1 is secant theta. And then dx is 1/2 secant squared theta d theta. So what we've got is secant theta over tangent theta d theta. Let's see what this is in sines and cosines. So secant is 1 over cosine. Tangent is sine over cosine, but it's tangent in the denominator. So this is 1 over sine, which is cosecant. Okay. What is the integral of cosecant theta? Let's go to our table of integrals. That's natural log of the absolute value of cosecant minus cotangent. So natural log of the absolute value of cosecant minus cotangent. Very good. So now we need to convert back to x. Okay, so we said that tangent theta is equal to 2x divided by 1. Tangent is opposite over adjacent, so opposite over adjacent. Therefore, the hypotenuse is the square root of 4x squared plus 1. Okay. Cotangent is so opposite of tangent, so 1 over 2x. Cosecant is the opposite of sine. Sine is opposite of hypotenuse, so hypotenuse over opposite. Okay, so we've got subtracting these two, you've got okay, now we can simplify this a little bit more because we've got 1/2 times this entire expression, and so we can split up logarithms, right? Because right, so if you think about it, we have the log of this is 1/2 times some full expression. So we can take that out and remove the 1/2, and then we're left with natural log of 1/2 plus c, which becomes a constant. So what we've got is and that is the integral.